This is Yuki. I'm currently doing some research work at Fenbushi, and I wanted to, kind of have this research workshop as an opportunity for some researchers from different backgrounds, like him, from academics and other engineering heavy backgrounds, and basically a bunch of other different researchers from different places to share ideas and discuss about things. So I'm hoping that we can make a lot of the conversations be more flowing discussions and whatever. So again, feel free if any of you guys have questions to the speakers, researchers, and yes, just raise the hands. Can ask whatever you want. We'll also make sure to have any question times later on as well, so that we can clear up any confusions if there was from the contents. But yeah, just don't hesitate if you have any problems that you want to discuss about. So that's the intention here. Now, I guess just to kind of like go over the schedule for today, as Chloe mentioned, for the first part we'll have I think 3-4 guests who will share their work. And then later on, we'll have a dinner for like probably 30 minutes, and then come back and we'll continue and onwards. And I think for probably the later half of the conversation, it will be quite a bit of like maybe some prover coordination related stuff to some projects that will also share some of the ideas around. So yeah, basically a lot of stuff popping up. So please enjoy. Feel free to just ask questions whatever you want. And yeah, let's get this going. Now, first speaker will be István, who will be sharing about, I believe, the naysayer proof. Is that right?
Yeah.
Yes. So yes, it will be naysayer proof. I'll give it a round of applause.
Okay, so in the next 30 minutes, and as Yuki said, feel free to interrupt me anytime. So if you don't understand something, it's most likely not you but me. So yeah, I don't want to left anyone behind. So yeah, just feel free to raise your hand, and then Yuki or Chloe will give you the mic, and then you can ask your question. So I'm going to talk about naysayer proofs, which is already online. So if you go to this URL, you can read the paper, or just scan this QR code. This is a joint work with Noemi from University of Maryland and Max Planck Institute in Bochum, and with Joseph Bono, who is a professor at NYU and a research partner at A16Z. And this work was done at A16Z during the summer when we did our internship with Noemi there. So the motivation is that this is the takeaway message, is that you don't need to verify zero-knowledge proofs or proofs in general on-chain. This might sound crazy and stupid. I don't know if you see it in the background, but hopefully I will convince you that you don't need to verify them. And the reason we don't want to verify proofs on-chain is that because they are costly. So this is just an example it's a smart contract taken from Starkware. Not just, I don't have any beef with Stark, this is just an example. This also applies to ZK Sync, or it also applies to Aztec or whatever L2 you want to mention. So as you can see, hopefully in the first rows, you can see this smart contract in the last 3 months burned more than almost $200,000. All this smart contract does is just verifying proofs. And so the bottom line is that verifying proofs on-chain is costly. And the other observation is that most of the time these proofs are correct anyways, due to financial reasons or reputation. You don't want to harm your reputation, so you will not post invalid proofs anyway. And the idea is that 99% of the time these proofs are correct. So we only want to interact with the blockchain if there's an incorrect proof. And our observation is in this paper, what we make is that it's way more efficient to prove that the proof is incorrect rather than checking the proof directly. So I will give you some examples later, and then it might be clearer. Okay, so for this audience, this table might be like trivial. This is just to give you an idea. Like if you want to verify a Groth16 proof or Planck proof on chain, it might cost you like $8 or something. Like these are gas prices taken a few days ago. The exact numbers doesn't really matter. The idea is that if you want to verify these proofs on a daily basis, like if you're Aztec or I don't know, Starkware or something, then you need to verify these proofs like dozens of times per day on a daily basis, and you will burn like lots of dollars. Okay. So what is our system model? So we have a prover Pablo Picasso, and this prover wants to prove some statement to the verifier Vincent, but Vincent is a great painter and he's busy painting good stuff, like this Starry Nights, which you can see in New York City. But so Vincent is busy with his painting, so Vincent doesn't want to check the validity of this proof because he has better things to do. So what Vincent does is says that outsources the verification of this proof and says to this naysayer, it's kind of like a word joke, I don't know if so most of us, English is not our first language, but in English the horses say nay. Okay. In Hungarian they say nihaha. Anyways, but the horses in English say nay. So if the proof is incorrect, then this horse will send a proof showing that this proof is incorrect. But we define some delay, some time parameter, and we only accept such naysayer proofs within this time parameter, let's say 1 day or something. And yeah, so the proof, and the naysayer will only come if and only if the proof is incorrect. Okay, so what do we gain? What we gained is that 99% of the time we don't do anything. If the proof is incorrect, we don't do anything. We don't touch the blockchain at all because we don't need to do anything. If the proof is incorrect, then there will come a fast and furious horse, and it will send us and save us with this naysayer proof. Okay, so we cut the costs of verification like by 99.9, but we have some added assumptions. What are the added trust assumptions is that now we need to assume a bounded delay model. So if there's no bounded delay, let's say the adversary, the NSA or KGB or CIA or whatever, can delay arbitrarily the messages, then we are screwed because this naysayer proof will not arrive to the blockchain in a timely manner. And if it would arrive after the time bound, then we are screwed. So we need to assume like a synchronous communication model. Obviously, we need to assume that the underlying blockchain is censorship resistant. If the miners doesn't want to include these naysayer proofs, then again, we are screwed. And we also assume that there's at least one honest horse who watches the blockchain and will send this naysayer proof. Okay, so this is some really simple formalization for you. So with the given, do I have a laser? Okay, anyways. So a naysayer proof only makes sense in relation to NIZK, a non-interactive zero-knowledge proof. So given an NIZK pi, we define a corresponding naysayer proof. And this naysayer proof will have 3 algorithms, the naysay and the verifier nay. Most likely you don't really see it. The one important thing is that you should notice is that the naysay algorithm sees the instance and the pi. So we assume that the naysayer somehow already have access to the proof instance, the proof itself and the instance. And the naysay algorithm outputs this proof pi, and the verify nay algorithm will take as input x, pi, and the naysayer proof, and will output 0, meaning that the original proof is incorrect, or will output bottom, that meaning that we cannot decide whether the original proof was correct or incorrect. Okay. I have some correctness and soundness definitions, but it seems that I lost some of you, so maybe I will just skip it. Informally, correctness means that if there's an incorrect proof, pi, then an honest naysayer should be always able to convince the blockchain that the proof was indeed incorrect. And the soundness in this case means that if there's a correct proof, then no adversarial naysayer should be able to convince the blockchain otherwise, only with some negligible probability. Okay, so this was just, it's super simple stuff, it just looks complex, but maybe you wanted some formalization after, I don't know, 5 p.m. Okay, so some frequently asked questions, like what's the difference between naysayer? I mean, feel free to interrupt me anytime again. So usually the questions I got is that what's the difference between naysayer proofs and fraud proofs? So fraud proofs, if you know this notion, what they do is that there's a computation and there's this bisection game between a prover and the verifier, and they try to locate in the prover's computation the point where they disagree. So again, they work over the prover's computation trace, and instead naysayers try to locate the disagreement in the verifier's circuit. So, and as you can imagine, like in most zero-knowledge proof systems or proof systems, the verifier circuit is way smaller than the prover circuit. So generally what we expect is that the naysayer proofs will be much faster than fraud proofs because we don't work over the prover circuit but the verifier's circuit. Okay, so why storing proofs at all? So you could say like, if we are optimistic, then let's be super optimistic or optimistic squared, and then we wouldn't have any proofs at all. Well, that wouldn't really work, so we still need some proofs in place. Because if there was no proof on the blockchain, then we cannot really catch the liar, like, right? Because there's no, like, the naysayer should re-execute the computation and everything. And re-executing the statement and the proof is way more costly than just checking the proof off-chain. Okay, so can you give me some examples of naysayer proofs? Yeah, wait, 2 more slides. Is there naysayer proofs for, so is this a meaningful notion? Like is this a meaningful notion? And I will show you that every MP language has a naysayer proof. I mean, the precise statement is the following. So there's a really classic result from the 1990 or 1991 by Weigel, Lapido, and Shamir, and they prove that for every MP language there is an NIZK that uses graph tree coloring, and so given this specific NIZK, there exists a naysayer proof which is constant time verifiable, and also the proof is constant size. So basically the naysayer would just point to the edge in the graph where the graph coloring fails. So that's like it's really easy to show that the graph tree coloring is incorrect. Like you just the naysayer prover would just, hey, this edge is not colored correctly. So now we basically prove that for every MP language there's a constant time and constant size naysayer proof. Okay, so here are some examples. I have 3 examples today, like one with shuffles, the other one with fries, and the third is with post-quantum signature, sorry. Okay, so you don't need to know what is Fry. Fry is a polynomial commitment scheme, and it's used extensively today on the Ethereum blockchain. So if you know what is a Merkle tree, you are fine. So basically, if you just zoom out, what the verifier does in Fry, it just does a bunch of hashing. I'm not going to get into the details, but it doesn't matter now. So the verifier just does log squared. So if there are n leaves in this Merkle tree, the verifier needs to do log squared n roughly hashing. So this would be the cost of verifying a single Fry polynomial commitment scheme opening proof. But instead, if this proof is incorrect, it's really easy to show that this proof is incorrect. the naysayer prover can just point to one of the nodes, intermediate nodes in this Merkle tree, and say like, hey, this is where the hashing fails. Or if you hash these two nodes, then you will not get the parent node. So again, the original proof size is log squared size, but the naysayer proof size is constant size, and also concretely much more efficient to verify on chain. Okay, so a shuffle proof is like if you have n commitments or Algamar ciphertexts, and you want to shuffle them, and you can create a proof which says that these two lists are basically the re-randomization and the shuffling of each other. And the current state of the art gives you a square root n-sized proof. It's a paper from 2012 by Bayer and Grove. And so know that if you have like, and Ethereum would like to do something similar that will use verifiable shuffles. So it's a language, it's a proof system that we really care about, because in, who knows, 10 or 5-10 years it will be used on chain. So, and if we have n participants, then the proof size is square root n, so really large. And kind of this is the state of the art. It's not really true, but I'm not going into the details. So the proof is really large, and also the verifier time is like on chain is unbearable. So if you have like hundreds or thousands of validators, you need to do like 4 times this number of exponentiations in a smart contract, which is like not gonna happen. So instead of verifying that this proof is correct, this proof of verifiable shuffle, it's way easier to show that this specific shuffle is incorrect. Basically, the naysayer could just point to two elements in this list and say that, hey, these two list elements are not correctly shuffled because, and then the naysayer will tell us why it's not correct. Note that there's a single syntax, there's a nuance here, because we assume in this case that the naysayer prover knows the discrete logarithm of one of the shuffled elements in the list. Okay, we can talk about it maybe during dinner. So another application that we came up with is post-quantum signatures. Like recently in the last few years, NIST, the National Institution for Standardization, they standardized a bunch of post-quantum secure digital signatures, and they are also interesting for us Ethereans as we march towards account abstraction, because in the future users could define their own signature scheme, whatever they want to use on chain, and it's likely that some of us want to use digital post-quantum secure digital signatures. And Sphinx is one of these signatures that were standardized by NIST, and the downside of all these post-quantum signatures is that they have large signature sizes and or public key sizes. So again, like these are the numbers, you can read them on the slides. And also in Sphinx is really similar to Fry in the sense that if you want to verify a Sphinx digital signature, what you need to do is you just need to do a bunch of hashing. Like in this case, you just need to do 67 hashing. But if you don't want to verify this digital signature, what you could do is if there's an incorrect Sphinx signature, you could just point to the index where this hashing fails. Again, the naysayer proof will be just 2 elements and a single hashing operation, which is on chain is really efficient. Okay, so what are the storage considerations? If you remember, I told you here, like a few slides ago, okay, maybe it's not worthwhile to go back, but we assume that the verifiers, in our applications, the naysayer verifier would be a smart contract, most likely. The verifier has as input the instance X and also the proof pi and the naysayer proof. And this is a little bit problematic because, so today, so this is not the right audience, you all know this, that in Ethereum we have like kind of 3 types of storage. We have persistent storage, call data, and data availability service. thus. And usually we don't use the persistent storage to store proofs because it's too expensive. So rather what projects like Aztec and Stark and all these nice projects do, they store all these proofs in the call data. But the problem with the call data is that it's not persistent across transaction calls. So let's say that the prover puts down onto the blockchain the proof in the call data, then this proof will not exist by the time the naysayer would come along. So that's problematic for us, but in the future, the vision is that there will be some so-called data availability services where we could store the data, the proofs, and on chain, instead, we would have like a polynomial commitment or vector commitment to the proof. And then the naysayer could basically open this commitment to certain positions and prove some statements about the proof itself. So kind of that's the vision, how we envision that this paradigm could be used in the future of Ethereum, because now it cannot be really used because the call data is not persistent across different transaction calls. Okay, so if you are interested in a practical implementation of naysayer proofs, or you would be interested in deploying this on Ethereum today somehow, then hit us up. Yeah. And okay, so some future work and food for thought for you, developers and researchers. So I think naysayer proofs might be interesting also on their own as a notion in complexity theory. So it would be nice to prove statements about the complexity of the naysayer prover's efficiency or verifier's efficiency. If you can come up with other interesting applications for naysayer proofs on Ethereum today, let me know. I'm interested to hear your ideas. For instance, a stable matching, like it's easy to show that the matching is unstable, or in more general, any language in CoNP might be interesting for this naysayer paradigm. There might be many extensions to naysayer proofs, like interactive naysayer proofs, probabilistic naysayer proofs with non-zero soundness error, and so on. Sky is the limit. And obviously, if you want to deploy naysayer proofs in practice, then it would be necessary to have a proper game theoretic analysis, because for an incentive compatible deployment, there will be like many parties, there will be provers, naysayers, and so on, and without incentives, there will be no proper deployment of this proof system. So if you're a game theoretician and want to think about it, I'm super excited to talk about it and think together. Yeah, this is our email, yeah, or we can just chat during dinner, and I will be also here the whole week. Thanks for your attention.
All right, thank you very much for the naysayer proof. Oh, I guess I was going to ask a question, but I think Mauro is probably, so please.
Yes, I have a question. I'm not sure if you already thought about this, but in the case that someone submits, let's say we do a rollup with this, and you detect a fake proof, and you submit that fake proof, how will you handle the state? Like, you will just have to revert everything? Can you do something more, maybe say, okay, just this is wrong in particular, so don't go around trying to restart everything?
Honestly, I haven't thought about it much. Like, it's really application specific, but so your question is like, in case of a roll-up, like we should just roll back the whole batch of transactions, or just a single transaction? That's the question?
Yeah. If you have to know how to handle those cases, or maybe outside the scope, no problem.
Like, we are academic people, so we can just say we leave this for future work. But this is really, it's a good question, don't get me wrong, but it's really application specific consideration. So, and it's hard to, it's not something that you could generalize, like, I don't know. So we didn't think about it, it's a good question, and I guess what I would do, I would just roll back that specific transaction if you can locate that specific faulty transactions. But the thing is that there might be multiple faults. So yeah, and so we didn't go into the weeds of all these practical considerations, but EigenLayer suggested this to work on during the week. So if anyone is in the EigenLayer house research or programmable trust house, and if you're interested in working on this, yeah, like you can think about all these practical considerations that Mauro brought up. I don't have a good answer, but I think it's maybe there's no good answer. Like it feels like more of a engineering problem to me.
Okay, perfect. Thank you.
Provable by ZK, and let's call it IP. Is your result kind of like specifying? Is your result basically can I interpret as specifying some properties of a co-IP? If so, how can we formalize it? If not, why not?
It's a. So you are saying that naysayer proofs give some kind of.
That gives me the impression is like because you're proving something opposite, right? So you actually by the end you mentioned the co-NP. So I'm just thinking about this co-complexity class, like how we formalize this thought, how we can generalize this result.
Good question. I don't know.
Future work.
I mean, yeah, that would be the hand wavy answer. Yeah. It feels super related to anything QNP, QIP, but we didn't. I mean, I'm not a complexity theoretician, so. But I would feel that all those results that characterize as co-IP or co-NP could be related to the complexity of naysayer prover verifier complexity. Yeah, I mean, if you want to think about it, I don't know.
Well, actually, let me throw you an easier question that you can maybe answer. But I think it might be a bit more context specific here. But have you kind of like delved into what's the kind of a time bound for formalizing this like naysayer jumping into the like nay?
I think this is also super application specific. So I don't think there's a universal bound you can give for every application. Like this should be the time parameter that is used by rollups and
or I guess maybe like some experimental evaluation of like, let's say if we do apply this type of things on some ZK VM or whatever rollups out there might be, or maybe even like just some ZK application.
So currently there's no implementation of this as far as I know, and so yeah, there's no. I don't think there will be a universal bound in the first place. In the second place, it will be super application specific. I mean, there will be many factors to consider. So it again seems like another roadblock to deployment of the system, that how to choose this parameter in a way that we can ensure the soundness of the proof system. Because you don't want to make it too large, because then you can roll the state quite slowly, but you also don't want to make this time parameter really small, because then maybe the network will be congested and then the naysayers cannot submit the proofs. Yeah.
I guess something interesting that I also kind of want to point out is that because like currently a lot of the ZK rollups kind of spend some time window to batch the proofs and then roll down to the proofs as of right now anyway. So to that point, like having some time window as a way to kind of reduce the re-execution cost, could be an interesting exploration for those who already, in terms of actually submitting to an L1. And in contrast, you could also explore with the likes of naysayer proof to essentially execute that with the maybe same latency or even less potentially. But any other questions here? Oh, there you go.
Yeah, this might be a little bit of a dumber question, but essentially what's going on here is like you're just posting the proof and then potentially executing it later, so it's essentially optimistic.
You're not verifying. Sorry, you are not executing.
Or verifying it later. Yeah. Is there like a granular difference between just like are they just re-executing the proof, or is the naysayer proof a completely different computation?
So most likely what the naysayer will do is just try to verify the proof of chain, and if it accepts, then does nothing, like sit back, relax, and enjoy life. If the proof doesn't verify off chain, then you try to locate in this verification circuit. Let's say like in case of Plonk, you have, I don't know, 3 pairing checks, like which pairing checks failed, for instance. And then you could tell the smart contract that, hey, try to execute the second pairing check because it will fail. And then the smart contract will re-execute only that specific check. I'm not sure if this answers.
Yeah, that definitely answers. And is that just an efficiency thing to only check that one part?
Yes, and you only check it when the proof doesn't verify. Because currently, like today, right now on Ethereum layer 1, you check all the proofs even though they will verify. So you could save like 99.99% of the work. Plus, even in the malicious case, you would do only a percentage of the verifier's work because you just check a single step or a few steps.
Very cool. Thank you.
Is it possible to do a naysayer proof inside a ZKP to prove that a snark failed?
What do you mean by signing?
Inside a proof set. So I have Plonk proof here, which is failing. And I want to recursively prove that that failed inside another proof.
Ooh.
And you don't need a VM.
I see. Sounds cool.
Sounds cool. I don't know if it's possible.
So you mean like recursively you want to prove that?
So I'm going to try and recursively verify proof A. If it fails, I want to prove it failed. Which normally, if you do like an aggregation scheme, the circuit just fail if you try and do that.
I think it's possible. You just show that the result of your pairing is non-zero, right?
But that the whole batch would fail, so
We don't want the batch to fail. We want to prove that one transaction
I see.
has a bad proof.
Alright.
We'll talk to you later.
I hand it over to you.
All right. One more question, maybe? One more question? All right, there you go.
I know you touched on this briefly, but what are some of the applications that you guys are imagining to use this naysayer?
I think one cool application could be Ethereum wants to use like verifiable shuffles in a single secret leader election protocol. And all these verifiable shuffle protocols are really beefy. So that could be like a cool application, or rollups, digital signatures. These are the applications that are in the paper and also what I was talking about during the presentation. But if you have any other idea, let me know. I'm interested to hear. But these are the 3 main application scenarios we were thinking about. But yeah, if you have any idea, hit me up.
Actually, maybe one more question we can have, if anyone has questions here. All good? All right. All right, again, thank you very much for the discussion. We have Ismael from Lagrange lab to share about the work that they're working on at Lagrange on ZK-MapReduce.
Full house. I really like this. I feel like a lot of the people don't go to the talks at the day conferences, so it's nice to have so many people here. So, hang on, how do I advance slides? Just with this? Awesome. So, for those of you who don't know, my name is Ismael. I'm the founder of Lagrange Labs. Our team builds infrastructure to make it efficient to verify data parallel computation, so things like SQL, MapReduce, RDB, and zero knowledge,
when run on top of on-chain commitments of data. So broadly, the way I like to articulate the application of zero-knowledge proofs in the blockchain context is as a mechanism when we're not talking about zero-knowledge, probably we're talking about solely succinctness, to shift the safety of computation away from a low-trust verifier onto a high-trust, a low-trust prover onto a high-trust verification environment. So an example of that is when you, for example, want to have a large amount of transactions that are executed by some off-chain actor to update some state, and then you want to verify the proof of the correct update of that state back on-chain, for example, in the context of a ZK rollup, where you're shifting the assumptions onto a high-trust verification environment away from a lower-trust proving environment. So when we look at the applications of zero-knowledge in the blockchain context, typically we are today looking at things that increase the abundance and the privacy of block space, and we're seeing a shift just in terms of how people are applying it towards things that I would say increase the safety of data access as well as the expressivity of what we can encode in a given transaction. And this is sort of the shift that we're seeing in terms of the newer applications being developed, being things like coprocessors, VM extensions, non-EVM execution environments, ZK interop, and more. So. And what do we mean by, for example, the expressivity of a transaction? So we look at what we typically encode in the state transition today. It is often just a simple exchange of value on an execution environment or a simple state transition. We look at, for example, the future state of what people are looking to encode within a specific transaction. There are things that are a lot more expressive. They're asynchronous computations that can be run using on-chain state. They are verifiability of things that are too large to put within memory of the chain. And they are computation that spans both single chain and multi-chain data that would otherwise be infeasible because of gas constraints in the execution environments. So this is how we can take the concept of transaction and have this be extended to encode more robust sets of computation. And so this is what kind of we get into what Lagrange does. So Lagrange focuses on what we call ZK-MapReduce, which is a proving system that our team develops that allows us to verify large-scale data parallel computation that is run on top of data encoded within a block header commitment. So storage, receipt, transaction data. So in the lingua franca that we usually talk about nowadays would be something like big data coprocessing. And the impetus behind this is if we look at, for example, the amount of data that's being created nowadays in the multi-chain, the modular, and the roll-up-centric context, we have more state data than ever before encoded on-chain, but typically the majority of execution environments can't access that data at the point of transaction. So really we can't verifiably search, compute, or query across really any meaningful amount of on-chain state that's not immediately accessible in the execution environment by function calls or just direct memory reads. So this is where we get to ZK-MapReduce and some of the work that our team does. We take a lot of principles involving either recursion or abstractions of recursion like folding, and we develop distributed proving systems on top of that that allow us to, in more performant ways than are currently possible, construct very large proofs that have some very interesting properties that make them well suited for large computation over large subset of commitments. And so this lets us what we like to describe as data lake style computation that's verifiable over on-chain state. And so what is required to generate a proof? You basically need to define a data frame the same way you would in Web 2, and then you need to specify a computation you want to run over that data frame. And the requirement set that we put forward is that this is data parallel computation. So things like SQL, MapReduce, Spark, RDB, and once we do that, we can verify it back on chain within an execution environment. So how do we do this, and what is the underpinnings from a cryptography standpoint of what we do? And so our team at SBC this summer put forward a new paper called Rect Proofs, which is a vector commitment scheme that's designed to prove batch set inclusion over any arbitrary data structure, and dynamic MapReduce computation over the subset of data within that structure being proven. And it has a very interesting property that we have not seen in previous vector commitment schemes, and that property is updatability. So why do you want a vector commitment that's updatable, and what does that actually unlock in the blockchain context? So Let's think about the idea of a batch proof with computation over the data that's being proven. So in this example, we're going to talk about volatility of an asset. So you want to, let's say, derive the standard deviation of the price of an asset over some ring buffer K of on-chain state, such that you can do a Black-Scholes and compute the price of an option. So you're going to start from block n to n minus k. You're going to prove the inclusion of the relevant leafs within each block, and then you're going to prove that you can verify the oldest block by the chronology of sequential hashing that gets you to the most recent block. All right, well, a new block comes in 12 seconds later, or faster if you're talking about a rollup, and you want to reuse this proof. You want to update it to account for the new change in price. So in this situation, if you were using a naive batch proof, or a snark of a naive batch proof, you would have to recompute from scratch that entire ring buffer K, all the inclusion and all the computation over that data. This is obviously not performant, as the amount of computation you have to do is linear with respect to the amount of data and the size of the data frame you're computing over, which is a pretty terrible paradigm if you think about it, because it doesn't suit itself well. As you compute more, it just grows linearly in terms of proving time. And so this is where our team has brought forward the reg proofs, which is a batch proof that's updatable in logarithmic time. So in essence, the amount of recomputation that's required is proportionate to the change rather than the actual size of the data frame. So in this situation, you would just remove the portions of the proof from the oldest block, and you'd reinsert something for block n plus 1. And so this works very well in blockchains, since they're, by design, append-only data structures, and computation over storage is a very low entropy structure. The majority of blockchain storage across successive blocks does not change. So updatable proofs are highly viable in this context. And so we're going to now discuss a little bit of how we do this and sort of some of the innovations our team has brought forward in this paper. So think about a simple Merkle proof, a commitment or a Merkle tree commitment to an ordered sequence of values, where you can create the root through recursive concatenation hashing of adjacent values. I think most people here are aware of Merkle trees likely, and if you're not, this is a nice summary of it. And now we think of membership proof. You take the leaf element and you take all the adjacent values from the leaf up to the root, the adjacent branches, and you just recursively concatenate and hash them to prove inclusion. And so let's say you update something in the set or the subset, such that the Merkle proof you've had for the previous commitment to data is no longer valid with respect to the most recent commitment. Well, you can update your Merkle inclusion proof simply in logarithmic time by just changing the portions of the path that have intersected with the inclusion proof that you previously had. So that's straightforward. And now we think of a naive batch proof. And you can think of a batch proof as an inclusion proof that demarcates the minimum path required for the inclusion of all the leaf elements that you're opening. If you were to do that out of circuit, it could be updated. But if you do that in a circuit, then you of course can't update that without recomputing the circuit. And you can't just by design do this in an execution environment because you're just going to run out of gas. So this naive batch proof really can't be updated if done in the snark. And so that creates a limitation when you're trying to open a large number of elements within a commitment. And so this is a concept our team brought forward called canonical hashing, which defines every branch proof as the subtree of nodes rooted at that position in the tree. And by defining the node subset within the witness, this gives us the ability, when something in the set that we're computing, or the subset that we're computing over, or the set that we're computing within changes, to solely update the subtrees that have changed without having to update the entire batch proof. And so what this allows you to do is to have logarithmic time updates of a batch proof done in zero knowledge. And it does not just include the inclusion, it includes a map-reduced computation on top of that inclusion. So as you open those elements and you progress up the tree, you can prove both map steps at the leaves and reduce steps at the intermediary branches that can also be updated in logarithmic time as the data that you're computing over changes. And so this is very, very good for computation over very large frames of data that have low entropy, which is what blockchains by design are. And so this lets us scale proving not through recomputation, but through recomposition of proofs. And this lets us have a very low overhead of supporting new chains, as we in essence solely need to update and verify historical proofs, and we don't need to cache intermediary, for example, historical blocks on every chain that you're supporting. And so in terms of the performance of this, in our paper, we're 135 times faster than naive approaches, involving like Merkle snarks and more traditional batch proofs. But we expect it to be a lot higher when we're just talking about data structures that are a lot longer in computation, like MPT trees. So for production MPT trees, I expect them to range of several thousand times faster. And they're fully parallelizable, since everything is data parallel, which means you can just distribute these for up to 10x or more improvement in efficiency. And verification time is also substantially faster, as proof size is smaller as well. And so we're now going to talk about some of the use cases of what this unlocks. I think it's intuitive here how this is useful for like ring buffer-based applications, which is where you want to compute over some frame and just slide that frame along the blockchain as the blockchain updates. Like volatility, standard deviation, price, etc. But there's some interesting things you can do here that I would call non-trivial that are exciting. So one of these is the concept of a digest transformation. So one of the things our team believes is that zero-knowledge systems are fundamentally going to become modular. So you're not going to have if an end-user application that uses zero-knowledge, likely it will have a downstream dependency on another application that uses zero-knowledge, where there are different parts of a full proving stack that your team or your company might have internal to it and might have external. And so one of the things that has historically bottlenecked a lot of proving over EVM-based data structures is the RLP encodings and the catch-back hash functions. And so what our structure allows you to do is to, in essence, take a portion of a snark unfriendly structure and continually keep it provably equivalent to a snark-friendly structure, which means that a downstream application that doesn't want to have the dependencies of computing over a snark unfriendly structure can simply just take a proof from us and a snark-friendly structure that has the same commitment to leaves and compute over that. So for example, you can take the MPT tree, built with Ketchak and RLP, and you can prove its equivalence to, for example, a binary Poseidon-Merkle tree with some ordering of leaf values, and then all downstream applications can compute over the binary Poseidon-Merkle tree instead of computing over the MPT tree. So you can, in essence, amortize the computational work to prove inclusion over the MPT tree to the updatable system, and have everyone else downstream building ZK-VMs or coprocessors or rollups or whatever they want, just compute over the snark-friendly one. So another one, more application level, you can do things like verifiable rewards just by taking a bunch of transaction data, doing a full index on that, and doing some filter operation to determine users' viability or eligibility for some reward structure. And you can structure that as SQL computation. Another thing that we're very excited about that's a little bit more in the weeds is what we call an updatable BLS aggregation. So as many people here are likely aware, if you're doing a BLS key verification, the aggregation time is typically linear, the verification time constant. So if you're constructing a very large BLS aggregation for a large number of keys that are signing successive things, you should generally ask yourself, how many of these keys have overlapped from the last signer set? If there's a high overlap of signing keys from, let's say, signer set X to X plus 1, then you really don't need to compute all of the public key aggregation. You can basically prove both the inclusion within the commitment to the signer set and the aggregation of the public keys in a rect proof, and then simply update that rect proof whenever you want to change a signer set or a signer subset. Or the signer set changes, since these can be updated as a set changes as well. So another thing you can do with this is what we call full storage queries. This is one that we find very exciting as well. Basically, if you think about an NFT contract or you think about a ERC20 contract, it's very difficult to have any type of computation that spans the majority of the data in the tree. So if I said, I'm going to encode a mapping on chain of address, it would be index of the NFT, for example, owner address, and a bunch of metadata, and I wanted to search by a downstream metadata, the only way to do that would just be to iterate the execution environment through all of them and check that position and then filter. You can't search by a secondary or tertiary value in a mapping. So this is a pretty big limitation if you're a contract developer, because it means you can't say something like, how many people in my NFT contract have a blue elephant, or how many users have an asset balance of greater than X in an ERC20 token contract. And these are very simple queries you could do in a database, but just how we structure data on the blockchain, it doesn't work very well. So this is something that we can do very effectively by in essence just keeping the portion of memory corresponding to the entire contract, just hot and a good data in a data structure that is performed to compute over, and then just structuring computation on top of that when we need to, ad hoc. And then you can also build some very cool DeFi primitives with this, where you don't rely on off-chain price feeds or off-chain oracles, and you just do everything on chain, where you're just computing a proof and verifying that proof back on chain of some synthesis of historical data. And so for those of you who are interested, we have two resources that I'd suggest people reading who find this stuff cool. First one, the Rec Proofs paper that our team did at SBC this summer. And second one is some work by Nick on our team that combines ZK-MR and Rec Proofs with folding. By design, since we're a company that believes that you should fundamentally be proving system agnostic, we build our constructions to support anything that has recursion or the abstraction of recursion, like folding. So our Rec Proofs and our ZK-MR system supports both, and it's just a question of performance for either, depending on use case. So that's the talk. Any questions? I think I'm a little short on this one, so I hope there's a lot of questions.
Yeah, so any questions? I think Mauro was looking at it very closely, but seems like you have a... Oh, you good? Okay, very good. Oh, okay, cool.
No questions?
All right, so I think Ying has a question.
Yeah.
Thank you for the talk.
Thank you.
Probably a naive question,
Mhm.
but yeah, most of your illustrations are like binary trees. I know that's like simplified illustrations. So how do you think Rec Proofs would interact with vertical trees?
Yeah, we can support any structure really. I mean, I think Rec Proof's a vector commitment, right? So if you're building a vertical tree, you can just build your vertical tree to have vector commitments that are more amenable to the properties you want. For example, you can build a vertical tree using Rec Proofs, theoretically. So what Rec Proofs is very, very good at is taking a data structure, irrespective of design, and having a way to assert a batch inclusion on it that's very performant. So, as an additional point, so I mostly illustrate binary trees because they look better on slides, but you can support any array of tree you want here. So MPT trees are obviously an array of 16, so you can do that as well.
Yeah, go with it. Thank you.
All right, great questions. Any other questions that you guys have at the back? Anyone that have questions? Oh, here you go.
So I guess a lot of the benefit of this comes from the fact that a lot of the state is staying the same all the time. So, have you thought about just instead proving the state differences or looking at it from that perspective?
Yeah, it would be a lot less efficient because if you're proving state diffs between blocks, there's a lot of state diffs you're proving. So it's you have a block with several billion leaves, and you're proving, you have a state tree which is several billion leaves. If you're thinking of memory values, maybe more. And you have really an entropy of a couple thousand that are changed per block. So being able to just update the structure with a logarithmic to the amount of updates is a lot more performant than just trying to state diff. I mean, I find.
Actually, I have a question. What would it look like to prove the state diff with the batch proof?
Well, I mean, I guess if you were doing a state diff, you would just use batch proof as well, right? So you just prove that between two blocks that the main difference was whatever was included in the batch. I think you could actually just use this for batch proofs.
So I should really read Rec Proofs, but I was wondering about prior art. So I'm aware of a few efficiently updatable accumulators, for example by Alan Tomashko. So how does Rec Proofs compare with these prior constructions that also have efficiently updatable accumulators?
So Which construction? Is this hyperproofs? Because Alan was on hyperproofs, I think. Right?
It was like some kind of dictionary-based thing.
I'm not sure of the paper. So Alan's a collaborator of a few folks on our team on prior papers. So Alan collaborated, I think, on hyperproofs with Travon and Babis on our team. And I don't think hyperproofs is updatable. Actually, I know for a fact hyperproofs isn't, and I don't think balance proofs or point proofs are either. Actually, I know for a fact that. I don't know if there's anything that's coming out concurrently with rep proofs in the last couple of months that might also be updatable. But I don't think anything prior to like August is updatable.
Great. You raising your hand? No? So, oh, okay. Hey, any other questions you guys may have? Just leave it out for a bit. Okay. You guys seem hungry, maybe? I mean, the dinner is right after, so maybe that's why. Okay. All right. In that case, then thanks again, Ismael, for the great
Awesome. Oh, one more thing. We're hiring for cryptography engineers, so if anyone here is a cryptography engineer looking for a job, find me.
Ismael. We'll get started with the second half of the session, and as you guys expect, it will be also packed with stuff to go through. So, yeah, let's get started. Now, next up, it's Seun from Polytope Labs. So please give a round of applause.
Hello everyone, it's great to be here. My name is Seun, and I have a background working on core Ethereum, ETH core back in the day. Also was on the Polkadot team, so it's been a while. I'm going to be talking a bit about some of the research that I've been thinking about, and kind of the motivation as to why I joined the blockchain industry, which is really scalability, right? We've all been looking into the scalability problem. But I think that, and so more recently, is that the scalability problem is also the interoperability problem. And why is that exactly? If you wanted to scale a blockchain, you will find that, well, the only way to scale a blockchain is to sort of have multiple blockchains, right? This blockchain has a logical process, a logical compute unit. And so you want to basically horizontally scale, so you have multiple compute units. But if all these compute units are kind of siloed and there's no secure way for these compute units to communicate, then kind of we just got back to the same problem we started with, right? Because now we no longer have interoperable money, which was kind of the original vision. We wanted to have interoperable money on a global scale, okay? So, yeah, if we can solve scalability, then we solve it through solving interoperability. And yeah, it's kind of how I think about it. You search for the problem long enough, you arrive at this conclusion. Right, so we need to verify consensus proofs, right? Like, this is standard stuff. I shouldn't have to go through this. It's expensive because you have probably very large validator sets. Casper, I'm looking at you. And you probably have unsupported cryptographic primitives in there, some hash functions that are missing, or maybe precompiles with DLS that we've been all waiting for and haven't gotten yet. So we should then figure out a way to verify these consensus proofs off-chain and then present proofs for this verification on-chain, right? Like, that seems logical. But yeah, there's a few problems with this, and I'll get to that. But I just want to define what this means, this ability to do computation off-chain and present proofs for it on-chain. For you probably know them as a verifiable computation scheme, but we can also think of them as a coprocessor because they process something and then they push it on off-chain. So yeah, the naive VC scheme can be seen as a snark. I use naive because there are more complicated VC schemes. And so the reason why I say snark isn't that great is because, take for instance our Cassper FFG proofs, you have over 850k validators who are producing all these signatures. And if you want to facilitate like instant cross-chain messaging,
okay, sorry about that. You would have to be able to compute them as fast as the Cassper FFG consensus protocol is producing these signatures. We all know that it's impossible. But it's not just consensus proofs, right? Like if you had to bridge optimistic state machines, then you also have to verify the correctness of those transitions, which also seems impossible to do so for optimistic state machines. They produce blocks like every 2 seconds. And yeah, you guys already know the numbers on all this. So it's clear that snarks alone, I hope I've been able to convince you, they are alone insufficient for instant interoperability. So we need something else. We actually need something that's faster, something that's cheaper, and comparable level of security, right? Introducing blockchains as a coprocessor. Now, this actually is not my idea. This is from the Bitcoin white paper. And it says here, we can verify payments without running a full network node. The user only needs to keep a copy of the block headers and the longest proof of work chain. I'm going to rewrite this equation and make it much more abstract. We can verify work done by the network, right? Because if you have some virtual machine on the blockchain, it's doing some arbitrary computation. And a verifier just needs the headers of the blockchain and the consensus proofs, right? The signatures in the case of proof of stake, but also the proof of work, the longest header. So, let's call this the light client lemma. We move on. So, a blockchain coprocessor. Immediately we see that if everything is predicated on the consensus proofs, then our consensus proofs have to have high enough cryptoeconomic security. If your consensus mechanism is backed by a few million, then it's not really secure because anyone can basically take over the network with basically the amount of money. So low consensus or low economic security means it's easy to compromise. Example is the Sync committee, which only has like a few $1 million backing it. I expect to see that we'll see a Sync committee attack eventually. And putting that into ZK doesn't make it more secure, right? Like it's still the same, still the same thing. Okay, this is where it gets tricky. If we're trying to use a blockchain as a coprocessor, then how fast is this blockchain? What is the computation throughput, right? Remember, scalable blockchains have to have multiple sort of state machines. And all these state machines have to be enshrined because that way the consensus proof attests to the validity of all of the state machines. You can think of the beacon chain as a consensus system and the Ethereum execution layer as kind of being enshrined on the beacon chain. You can think of also the ZK rollups as sort of being indirectly enshrined because you can't post invalid ZK rollup blocks. So yeah, a single state machine forms this bottleneck and we need multiple of them. And also we should have cheap enough consensus and state proofs, right? Because if we want to verify the work that was done on the counterparty network, we should be able to verify the consensus of that network and of course state proofs of sort of the work that was done. This is pretty easy. Actually, you could just do BLS and aggregate them, roll up BLS, it's aggregatable. This APK proofs is actually a new thing. It was worked on by the Web3 Foundation researchers, which allows you to basically be unaware of the individual BLS public keys, but you can still see the snark proof that attests to the validity of the aggregate. I'll get into this later, but yeah. And if you wanted to do cheap state proofs, you could just do a Vorpal tree with, really you could do up to 1024, it doesn't really matter. So, we get into what Hyperbridge is. So we leverage Polkadot, and Polkadot is this instance of a consensus system that has multiple enshrined state machines. Right now it has like 50 parachains, but this number will grow into the future. And it also has, very, very high cryptographic security right now. So I already discussed this, and I can kind of get into how Polkadot achieves this multiple enshrined state machine. So actually, the validator set is sharded and assigned to each individual parachain. And what happens is, as these parachains produce blocks, first the sort of committee that's assigned to this parachain will check it, and then they will shard the data across the entire set. And it's kind of optimistic in the sense that the entire set will not check it until it is reported to be fraudulent. But of course, the entire set has the data to reconstruct the block and assert that it's fraudulent. But at the same time, the finality of the parachain blocks is kind of predicated on its validity, right? And if there was some consensus fault, then the committees and whoever was involved in that block basically get slashed. And Polkadot also has very cheap consensus proofs through this new sort of bridge protocol called Beefy. I won't really get into that. But we can leverage as many parachain cores for basically our computation. We can just basically assign work to all these cores and let them do work, and then we just verify the consensus proofs and some stake proofs for the output of that computation, right? And yeah, we can do some very, very interesting stuff by overlaying a Verkle trie on top of the classic base 16 tree. But of course, long time we want to probably enshrine that to the relay chain. So this is kind of the drawing that I had of Hyperbridge back when we committed to building it. And I can basically show you that this is a black box, but Arbitrum is basically trying to send messages to Optimism, for instance. Arbitrum has consensus through Ethereum. It doesn't have any consensus of its own. Same thing with Optimism, right? So you see consensus here between Hyperbridge and Ethereum is kind of two-way. Hyperbridge has its own consensus. Ethereum reads that consensus, and of course Ethereum has its own consensus, and Hyperbridge is able to read Ethereum's own consensus. And then it can basically facilitate message passing across all these different chains, and you can also add as many chains as possible. And this is all secured by Polkadot's own cryptographic security. But even better is that we can also run a full node of all of the connected blockchains. So this is where it starts to get different. Is that we first do consensus proof verification. Now we know what this is a canonical chain. Then we can basically re-execute all those blocks in the canonical chain just to assert that they're all valid. And then we can then start to do state proofs of the messages that are intended to be passed around. And for this, we're doing this fancy protocol. We have ZK-Caspa for the full Caspa FFG consensus set. It's the case that we don't produce ZK proofs of the signatures. We just verify the naive BLS signatures, but we have a ZK proof of the aggregate public key of the validator. And I'll get into the math of that later on. But we can, like I said, re-execute these blocks because Polkadot's going to have this like on-demand core time where you can buy blocks from the relay chain on demand, and we can basically shard the work of doing all this block checks across multiple parachains. Now, I believe that this is, of course, critical for secure cross-chain messaging from any kind of optimistic state machine, right? Because there's nothing stopping from a sequencer from posting an incorrect assertion, and if you're just looking at Ethereum's state and reading the L2's state from that assertion, you're most likely going to get lied to, and there's not even slashing for that. Hyperbridge allows for arbitrary message passing, so you can pass, arbitrary bytes around. We don't really care as long as you pay for them. And it could also be used to read on-chain state as well. Also, historical state, because we don't delete any blocks that are stored forever on our chain. You can always query them if you want to. And it's actually on testnet. We're connected to Sepolia and all of the L2 rollups on Sepolia. So if you want to try it out later, you can just come talk to me and I'll give you a small demo. So, issues. I think this is not the slide. Okay, maybe this is. I think this is present. No, that's not present. Present? Oh, yeah, that's fine. So I wanted to get into APK proofs for a bit. So just more formally, you have a set of signers. They all have public keys. The verified knows the commitment to the full set of public keys. And the prover just wants to prove that some aggregated public key forms a subset to this sort of full set. And they will sort of give the verifier a bit list, which represents the public keys in the subset. And there's going to be a proof, a succinct proof, that this APK is correct, properly done. You can think of this as a sort of summation with the bit list over the full set, but then the bit list is, of course, turned off whereabout there's no participation in there. And this is kind of what that looks like. You have a prover that just takes the bit list and produces the snark proof. And the verifier will have the commitment, APK, and the proof for the APK, as well as the bit list. And if the snark is correct, then it just outputs 1 or 0. So we get into ZK-Casper and kind of how it works. The expensive part is in Casper, which is actually in handling the public keys, right? You have, 850K validators, each public key is like 48 bytes, that's around 30 megabytes. That can never fit into a block, so no point even trying. What if instead we don't need to know the individual public keys, we only know the aggregates of the attestation committees? So I'm kind of glossing over Casper FFG protocol here, but the protocol basically splits up the set into attestation committees, and there's like 2,000 max in each. So we only need to know the aggregate of each attestation committee, and we do this snark proof check to assert that whatever aggregates you're giving to us, because we don't know what's in there, but you give us a proof that says that these aggregates are in the commitment to the entire set. And yeah, the verifier basically now has 0 knowledge, and the amount of data complexity or communication cost is now less. So they only handle the commitment, the aggregate of the attestation committees, the snark proof, and we just perform naive BLS signature verification because Polkadot can't do this. There's host functions for BLS signature checks, and blocks are cheap, so we can just throw as many signature verification checks that we need as in there. Which is really faster than trying to do ZK proofs of validity. We can basically beat ZK proof to do this. And yeah, this is kind of the core of the ZK-Casper protocol, and there's something clever in there that I'll get into later, but basically the proof is you have the attestation messages, the aggregate signature from each committee, and the aggregate public key of the committee. And this is kind of a set of tuples. And the verifier will do this APK proof check, right? It will take the sum of all the aggregates, because we have a commitment to the entire set, right? So we'll take a sum of all these aggregate public keys and check that this verifies. And then finally, we just do the check for signature verification. Now, if you're a cryptographer in the house, you will be asking, what about row key attacks? If we're summing elliptic curve points, then aren't we kind of vulnerable to a row key attack? Actually, no, we're not, because we have to do this check. This check has to pass, right? So say I'm an attacker and I wanted to basically do the inverse of the entire validator set, right? And I'm assuming we understand the row key attack, or I can just explain it, because this is supposed to be a discussion. All right, so in a row key attack, there's 2 signers, Alice and Bob. They both have public keys. Bob is going to try to convince someone who actually wants signatures from both of them.
It's very hard to see.
Damn. Okay, I can make it bigger. So we'll have a verifier here on this side. They are interested in a signature from both these signers. And how that kind of works is you will take a sum of the public keys of Alice and Bob, and then you do a pairing check with the message and the signature. But the problem is in this summation is that Bob could present their public key as the inverse of Alice's public key. So they will take the inverse of Alice's public key. So what happens is when they present that to the verifier and the verifier does this addition, it just works out to be Bob's public key. And they produce, of course, a signature with their public key, and the verifier successfully fooled that both of them have produced a signature that's valid, which is, kind of how that works. But we don't do any sort of summation here, right? Because whatever public key that is provided has to have a valid signature. So if you're trying to provide an inverse public key, you would also have to produce a valid signature for that inverse public key, which is hard. As long as you're not Peter Shaw with the quantum computer, you shouldn't be able to get the public key for the inverse, which is the discrete log problem. I can move on if there's any questions, or if there's not any questions. Okay, go ahead.
Go ahead.
Is it right without the microphone? Yeah. So you talk about the aggregate public key being like per committee and how you're updating it between each epochs. But my understanding of the shuffling is that is kind of uncorrelated between epochs per committee.
Yes, there is. Yeah.
Yeah. Could you explain how that works? Like, there's obviously something I don't understand.
So we don't actually care about who's assigned to what, because all we care about are that these public keys are in our set, the commitments. So we don't care.
Maybe the parts that were, perhaps just to add on that, is because in this context, the parachain itself would perform the BLS signature aggregations and verifications natively. So I guess maybe different from traditional ZK-like lens in that they don't actually generate proofs for every single signatures that attest to the consensus, but rather they already kind of have that verified natively within the parachain who basically perform the BLS aggregation, and then so they kind of like generate the proof around that whole aggregated BLS signature. That makes sense.
I think I understand, but you know, chat later.
Yeah, so I'll say the key takeaway is we don't actually care about the attestation committees. You know, as long as they verify, right, and they are in our commitment, because we initialize the process with like a trusted commitment, so the entire set, and we can also update this commitment because it's a KZG homomorphic commitment.
So you can share the same commitment between all the different committees. It's like that's a short answer.
Yeah, yeah.
Yes.
Yeah. So that was ZK Casper, and I will just basically run through a Merkle tree, and we can go into more in-depth questions. So a Merkle tree, basically you take the base 16 Merkle tree we all know and love, you extend the arity, you replace the hash function, use some KZG commitment, and you can now produce sort of constant size proofs for members in the branch nodes. And you can even take this one step further and basically combine all the proofs from all the different branch nodes, because you know in a classic hash function you kind of have to reveal the pre-image of the hash function to get back the same hash. But in this case we don't. So we can combine these proofs into a single proof using a batch PCS scheme, and we can achieve like basic constant size state proofs for any items in our state. Yeah. And now that we've sort of amortized the cost of verification, then we're basically cost competitive with MPC bridges that don't do any kind of consensus or state proof verification. Yeah, that's actually the end of my talk. If you have any questions, then I can take questions.
Yeah, I guess I think it's a lot of stuff that he went through, but any questions, please feel free to just raise hands and throw. I mean, any naive questions, okay too. Oh, perfect.
Thanks, a great talk. I wanted to bring back on the ZK Casper and the thing that we just discussed about the commitment. So as we established is that the commitment to the validators can be used for any committees, but is that supposed to be to verify membership of the validators?
Yeah, it's a membership check.
Right. And is it supposed to be verified in circuit? I think in your paper, in your article, you mentioned that it will be a custom gate that will, in every step, check that the validator is a part of this set in the committee. And is it possible to do that as a custom gate? And maybe you can provide some data on the performance.
So, I mean, the performance of this is in the original paper, and I've run this myself on my MacBook. And it takes 4 minutes for 1 million, so that's 2 to the 10, I think. Yeah, for 1 million validators. That's proof generation, right?
Is that creating the commitment or checking that the validator is a part of it?
Creating the proof. Oh, verification is a few milliseconds because it's a single parent check. It's a Plonk verification.
But if you do that in circuit, are you supposed to check that in circuit?
We're not doing it in circuit. This is going to be run, of course, natively on the parachain, on-chain, if that makes sense.
Okay, yeah, I see.
Yeah.
Yeah, I might have missed some stuff, but I think it might have been related to what Willem was asking. But how do you get away without verifying the committee rotations?
So yeah, I guess we have to take a step back and kind of understand that at the end of the day, we just have a set that's producing signatures, right? And as long as their signatures verify, and we can see that they are a member of our set, then we don't really care what.
I get it.
Yeah,
I see that now.
Yeah.
Okay. Thank you.
Try out our stuff on testnet, please. By the way, we want to get feedback, join our Discord, and yeah.
Great question, by the way.
I also joined the talk. I joined the talk like in the middle, so might miss something. But I'm curious that like your ZK-Casper or like can actually prove the historical ones as well, like because I saw your mention about like historical like data, but
Yeah, I mean, so because we do all this verification on chain and they're kind of stored on chain, they live basically on our chain forever. So you can always query information about historical, blocks on our chain. If that makes sense.
you have an aggregator on the about the blocks in.
Not necessarily an aggregator. You can think of it as we do a verification of the consensus in abstract terms, and the output of that is a verified header. We persist that header on chain, and it kind of lives there forever. And so anyone can always query state proofs associated with that header. Yeah.
Is it come from the ZK-Casper or like other?
Yes, it was an output from the ZK-Casper protocol.
Thank you.
Yeah.
Oh, sorry.
Hi. Sorry, I just had a question, actually, kind of extending from what Pio was saying. But are you kind of like performing? Like she was asking about like being able to check the historical state. So like historical state. So in the case of what you would be working with polytopes, like doesn't that mean that you have to also accumulate all of the block header that you have attested to via Polytope, and then with that history of block header, then you can say that okay, some historical data that you can access via your state proof, not like just arbitrarily old, I guess historical data. Is that correct?
So the thing is that every header actually is linked to all of its own historical headers, and this is an artifact of the beacon chain protocol itself.
I see.
Yeah, so,
Gotcha.
yeah.
Yes. So you were talking about this as kind of like a interoperability thing, right? So that means you're still gonna have to do some proof of consensus between like the hyperbridge chain and all of like the other chains as well, right? Or
Yeah, I think that was covered here, where essentially we stream our consensus messages or proofs to all our connected chains. So in this case, and I can talk about the economic model of this, is that we're subsidizing the cost of these consensus messages, right? So that these chains are always aware of our latest state, but then users of course have to pay for the state proofs that are associated with these verified headers.
Nice. Okay, yeah, I see what you're saying.
Yeah, because like in our state, there's the roots to Ethereum, so you verify the proof to Ethereum, and you verify parts of Ethereum state that you're concerned about.
But like, let's say Optimism wants to talk to Arbitrum, right? And then Hyperbridge is, I guess, like does the Optimism chain have to verify the consensus of the Hyperbridge chain in order to verify all the information of the other chains?
Yes, so I think of it also as like proof aggregation, so you can imagine all these different chains are connected to us, and maybe just their own sort of consensus systems, right? Hyperbridge becomes this meta consensus layer that is doing all this verification, but then any connected chain just only has to verify our consensus system, and we kind of proxy, using the like client lemma, the verification of all these other consensus systems.
Right, and then so like the reason why you like kind of built like your own parachain to do all of this is because like all of this is like pretty expensive to do, like
On chain,
ATM, right?
Yeah.
So, I mean, is it cheaper for an Ethereum chain to do the proof of consensus of like a Polkadot chain? Is that why you
Yes,
put
it is.
Polkadot in the
Yes,
middle?
it is.
Okay, that makes sense. Thank you.
I think the argument here is that the native VLS would be quite expensive to do on chain. So
On any kind of EVM.
yeah, any EVM.
And also there's also the speed, latency aspect of it all as well.
Any other questions? Oh, well, one more. Okay.
Let's go.
Let's go.
How does this relate to like a bunch of other efforts on like shared sequencers and stuff like that? Because it seems like this is basically kind of like a opt-in shared sequencer type kind of thing potentially, right?
I actually really love that you brought up shared sequences because I feel like that's something else that people are kind of championing as a solution to L2 interoperability. It's the case that no, they're not, because sure, you now sort of aggregated 2 state transitions and you posted that to the main Ethereum chain, but we still don't know if they're valid, right? Like we still kind of have to wait the challenge period.
Yeah, well, they haven't really solved the problem yet, but yeah. They're just putting all the data together, but I don't think they've actually solved like the cross-chain transaction problem.
Yeah.
So yeah, okay.
And I guess I'll also add that, like with shared sequencers, most likely you also have like, to begin with, a single entity that's also performing that shared sequencing role and upon which you have very different trust assumptions. Then let's say you have different parachains that is running on top of Polytope, for example. All right, so I guess that's the end of the Sean's talk. Thank you very much, and please give a round of applause.
And like come talk to me after, and I can also show you a demo if you're interested of cross-chain arbitrary forecasting.
Yeah. Next up, it's gonna be Diego from Lambda class. Woo!
Hi, hello. Hi, hello. My name is Diego, and I am head of research at Lambda class. And today we are going to be talking a little bit about the work we are doing at improving current start provers. And of course, then Mauro is going to give a talk on how we can improve these by making some changes to the current VMs. So this is an outline of my talk. First, I am going to give a brief overview of Starks in case you are not familiarized, and also to know about the things I will be talking, because I can say, well, we are going to optimize this, this and that, but we don't know where they fit in the protocol, so it's important to have an idea of the main steps. Then a short introduction to Stark Platinum, which is our implementation of a Stark prover, which is trying to be compatible with StarkNet's Tong prover. And then we will talk a little bit about the areas of field arithmetic, hash functions, of course something related to proof size, and then lookup arguments. So, Starks in a nutshell, Starks are scalable, transparent arguments of knowledge. This means that Starks don't need a trusted setup. That's opposed to different Snarks, which of course have their special setups, and you have to trust them. And Starks, since their security depends only on the security of hash functions, are conjectured to be post-quantum secure. So what are the ingredients of Starks? First, an execution trace, which is just a table containing the values of each register at each execution step. Next, Mauro's talk will go deeper into the VM and how it works, but let's think of this as just a table of values, and of course maybe we have also the values of the memory and all that. Then we have a set of polynomial constraints over the trace, which is the algebraic intermediate representation. There again the virtual machine will play an important role, because depending on the set of instructions which we choose, we will have a different set of constraints. Then what we have to do in order to prove is transform this execution trace and these polynomial constraints into some relationship between polynomials. And so what we are going to do is encode the execution trace as a set of polynomials that is done as interpolation by FFT. And then we will have to commit to this execution trace, and that's why we will have to build Merkle trees. And there appear the hash functions. And then what we have to do to show that the constraints are really forced over the trace is compose all the constraints and calculate some quotients, because that way we can get the succinct argument. And then what we have to show is that that effectively the resulting quotient is indeed a polynomial, and there we use the Frey protocol, which is going to recursively fold the resulting function and try to show that it is close to some low-degree polynomial. Okay, so these are like the main steps. In our prover, we have like 5 separate rounds where we kind of encode all these computations. So what's Stark Platinum? As I was telling you, it is our implementation of a general Stark prover. There you have the link if you want to look at it. We have a Telegram group. It's written in Rust. We wanted to focus on security and performance. As I told you, our objective is to make this prover compatible with StarNet's prover, and also as a drop-in replacement for other popular choices such as Winterfell. It can be used to prove code written in Cairo, because we have the Cairo VM, and this prover also has an implementation of the Cairo Air. And right now, as I was telling you, we're working towards full compatibility. So, what are the things we have to attack if we want to get to an efficient Stark prover? Well, the first thing is everything depends on field operations. So having like really fast field operations is crucial, because we are going to have to interpolate, evaluate polynomials, sometimes use even arithmetic-based hash functions. So the original prover worked over 252-bit field using basic Montgomery arithmetic. And we need that the field has like certain characteristics if we want to interpolate and evaluate polynomials efficiently. So in general, what we want is these fields to contain a large subgroup that is a power of 2. Of course, maybe we can do better, and right now the focus is shifting on smaller fields. This is an advantage of Starks over elliptic curves, since we can go over smaller fields. In the case of elliptic curves, to achieve the necessary security or everything, we need to work over a certain field. So in this case, for example, if we use the first prime, which is sometimes called mini Goldilocks, we have like special reduction formulas that are like more performant than basic Montgomery arithmetic, and also using smaller fields results in an advantage when you work with the VM, because right now sometimes the VMs have to represent certain variables with a field element that takes 256 bits, and here maybe with 64 we can just represent all the variables we like. Of course, another option is, for example, immersing primes, and so in these cases we get like smaller base traces, so the memory use reduces a bit, and especially we get like faster operations. Of course, one drawback that we have is that we need to achieve the necessary security, and so the field has to be of a certain size, and so in general we would have to work over extension fields. So for example, to achieve 128 bits of security, we will need to work with an extension 3 with mini Goldilocks, though some projects work with extension 2, and they are targeting more or less at 100 or 90 bits of security in general. So of course here we have a trade-off between using like smaller fields but then working over extensions, or working over a base field. Maybe we can find something better than the 252 start field. Then, of course, one of the other things is we have to build lots of Merkle trees, because we have to commit to several polynomials. For example, when we do Fry, at every folding step, we have first to commit to the polynomial. And so the problem that we have is that maybe generating just Stark proofs is really fast, but we in general want to patch like several proofs into a single one, and so we have to use recursion. So what we can do is like create a binary tree where we take, for example, each program, we compute the proof that we calculated it correctly, and then we take take two proofs and use a verifier to generate a proof that will verify those two proofs. That way, what we can do is apply, of course, recursion at each step and reduce and get to a single proof that attests to the validity of several 100,000 proofs, for example. But of course, when we have to prove that we verify the proof, what we have to do is verify Merkle inclusion proofs. And so the problem is that for Starks, traditional hashes such as Blake or SHA-3 are not arithmetization friendly, and so they add a significant overhead in proving time. So of course what we can do is, instead of hashing with those, we can use some other hashes, for example Poseidon or Rescue Prime, which are like faster to prove when we want to verify. But the problem is that they are much slower than the others. So, okay, we get like faster recursion, but still Merkle trees are like quite slow. So this adds, for example, significant overhead to the Pi protocol, since we have to commit to intermediate polynomials. But maybe what we can do is, for example, use some tricks like skipping Frey layers. So instead of committing to every layer in Frey, we commit every second or third layer. Of course, that reduces a little bit the soundness error. But what we can do is increases the soundness error. But what we can do then is, of course, do a little bit more queries and increase proof size. But that way, we don't have to do that many hashes. Of course, something that is crucial is maybe to have some kind of hardware acceleration for these primitives, and we believe that with that we can get a lot better than before. Well, regarding proof size, of course, there were like several optimizations that we saw across different implementations, and so we tried like to get them more or less together. The first thing is, of course, avoid sending to the verifier redundant information. So there are lots of things that the verifier can compute directly from the information the prover is already sending. For example, if we send two evaluations from the upper layer of Frey protocol, then we can compute one element of the next layer. So of course we don't pass the element of the next layer. And we can then check everything when we do the batch inclusion proof. Another optimization is that in general we have to pass two values for every query in every Merkle tree. And these values correspond to the evaluations of the polynomial at x0 and minus x0. So what we can do is, instead of having them in different branches of the tree, we can put them together, and so that reduces the number of authentication paths we have to pass. Of course, then we can also reduce like the redundant paths and send less information. Some other optimizations, of course, have to do with skipping Frey layers, that is to say, committing to every second or third layer, for example. And the basic idea in the Frey protocol was to randomly fold the polynomial until we got to a polynomial of degree 0. But what we can do is, instead of doing that, is finish before and just send the coefficients of a degree n polynomial and tell the verifier, okay, check with this polynomial. Because really what we want to do with Pi is not having to send all the coefficients of a very large degree polynomial. So what we do is we fold, and so we have to pass like less coefficients. Of course, degree 0 is convenient because it's only one value, but then since we have to do lots of queries, maybe it's best to cut before reaching degree 0 and sending all those coefficients, which will be much less than the information we have to pass from the authentication path.
I have a question.
Yeah.
By skip layers, by skip layers. Thank you. So skip layers just means like finishing with a higher degree. It doesn't mean, so it does mean like only committing to every other layer?
No, what you do when we say, one thing is finishing before reaching degree 0, and the other is skipping, which means that, for example, you started with a degree n polynomial, and then when you go to degree n over 2, you don't commit to that one, and then you jump directly to degree n over 4. Of course, you have to pass more elements from the upper layer, because when you skip, for example, if you don't skip, you have to send 2 elements from the upper layer. If you skip 1 layer, you have to pass 4, but the advantage is you don't have to commit to that polynomial, and maybe the total number of elements or hashes you have to calculate is reduced. So that's a common trade-off. I don't know if that answers your question.
It does, thank you. And how does that affect the security analysis?
In that case, there are like some proofs. It reduces a bit it increases a bit the soundness error, but in Fry, the final security depends on the total number of queries. So you can either increase the number of queries or maybe increase it by using, for example, proof of work. So maybe to get back those bits of security, we ask the prover to solve some sort of proof of work with a certain number of bits of security, and then we recover that. Of course, then we have proof recursion. That is especially useful because what we can do is always batch more proofs. There is like no security loss when doing recursion. That was a paper that appeared recently by, I think, Alessandro Chiesa and collaborators. And then, of course, if you like shorter proofs, you can always do like one final step of recursion, but instead of using Starks, maybe you can use a snark, for example, Plonk or Grok16. Of course, there you have like maybe some extra cost for the prover, but then the proof size is greatly reduced. And so, for example, I think the Polygon ZK EVM is using like this trick. Of course, there is one caveat that you are sacrificing your post-quantum security because these snarks are not post-quantum secure. And then, of course, there is another huge cost, which is related, for example, to memory consistency and memory checks, where you have to do some sort of permutation argument. And so, in general, that involves a graph product check. You have to sort a large vector, and then you have to compute like several inverses. So really, those are like expensive calculations. Even besides, when you want to do these arguments, you have to sample randomness, and if you want to work with smaller fields, then of course you have to sample your randomness from the extension fields. And then, of course, there are like some operations which are really expensive to prove in Starks. So you can use, for example, some specialized built-ins. Of course, right now, for example, in the Stone Prover, you have static built-ins. That means that you have like certain boxes of a given size, and you get to pay for the built-ins whether you use them or not. Or if you use them one time, maybe you have to pay for using it like 10 or 20 times. So that adds a lot of overhead. So there is a lot of study on how to work better with built-ins, either by having dynamic built-ins or dynamic layouts for built-ins, or maybe using like some other type of construction, for example, like chiplets or any other use. And of course, everything related to this is tied to the kind of lookup arguments we are using. And so right now, there is like a push for the logarithmic derivative lookup. And there were some improvements using the GKR protocol. So we hope that in a brief time, we will have an implementation of this and be able to measure the performance concretely. And well, finally, just a note on security. The security of Starks depends on 4 parameters. first the field size. So as I was mentioning you, the field size should be much larger than the low degree extension domain, that is to say the domain over which we evaluate the polynomials. And typically it has to be like the log 2 of the LDE domain, of the size of the LDE domain, plus the security level we want, the hash function, but in general using like ordinary hash functions with sufficient digest size is more than enough. And of course then we have the number of queries, which increases of course proof size. And of course then we have proof of work. Then there is like some discussion on which are the optimal parameters for Starks, depending on whether you work with provable security, which may be like super conservative, or maybe some conjecture security. Right now, more or less, the different projects are targeting more or less around 100 or 128 bits of security. And well, I think that's pretty much it. So thanks a lot.
Thank you, Diego. Any questions? Oh, perfect.
Hi, I'm having a question regarding the computation of this group size. So you mentioned that you have to pick up on the large coefficient rather than the small coefficient. Any reason behind that? And the subsequent question after that is, how can one be or one protocol be selective about the coefficient size while assigning to the polynomial?
You mean on the number of queries and all that to achieve the desired speed level?
Yes, yes. The rationale behind like means you told like you have to pick the large coefficient rather than the small coefficient while assigning to the polynomial. So
yeah, no, it depends on what you want to do. If you want to be like super conservative, you just stick with the provable security. But of course, what we have seen so far is that using conjectural security has not led to any noticeable attacks. So maybe you are just covering yourself too much, and maybe you can just work with smaller proofs. But in any case, if you want to be like super conservative and super paranoid and want to have your 128 bits of provable security, which you don't know really because there might be better bounds, there are still like several security analysis in Pride, then what you can do is continue recursing and then batch more proofs, and then in the end you end like amortizing the proof size. Or if you want, in the last step, just go for a snark, and then you get like your constant size proof, which is very short, and then you're done. So
got it. Regarding the recursion function, so like means do I have to put on the protocol itself, or is it something that's being auto-embedded on that?
No, that in that case, what you can do is just like code, for example, the verification circuit in the Cairo VM, then you execute, and then you get like the execution trace to verify like the proof, or the two proofs, and then you can use like the ordinary start prover. The only thing is you will need certainly to use some built-ins for the hashing, for example, to make it efficient. But the good thing is the verification circuit is always the same. So once you have it for two, then you can continue using it as long as you need to reach to the final step where you can use your snark, or you just obtain the final proof using starks.
Understood.
About the technique of skipping every other level in the Merkle tree, could you just give like one practical example of how that could be attacked? If I'm a malicious actor and I know you're skipping every two level.
No, the thing is, it works more or less like ordinary Fry. Maybe because the best attacks you have on Fry are interpolation attacks. You know you are free to choose like n different values in the Merkle tree, but then of course you have the blow-up factor. So the probability of you like getting a favorable query is like 1 divided by the blow-up factor. Maybe if you skip layers, there is like the chance that you might get luckier when jumping below, but I don't know, I should check maybe the security proof, or we can discuss it later, but there is like this analysis by several papers where some techniques reduce soundness. For example, another problem is when you use like this communication reduced version of Pride, where instead of sampling n different random numbers to perform linear combinations, you just sample one and then you calculate powers. Then that reduces soundness a bit, but really it's what most of the protocols use right now, and everybody more or less lives with it. So, yeah.
Thank you. Any other questions? Who's and by the way, I think it was a great question, just on the security front. Any other security questions? Anyone? Anyone who think that this skip just this shit doesn't work? Like, you know.
We're trying to be nice.
All right, trying to be nice. Okay. No, don't be nice. Be nasty. Just, you know. Anyone? All good. Okay, so I guess everyone thinks that this thing works. So all right. All right. So next up, we are gonna have Mauro, and then we'll have István. I think we originally had E and then Mauro, but I think just continuing from this talk, I think makes more sense that Mauro is gonna go first. So.
Okay, so this is working perfect. So, okay, so Diego has just shown to everyone a lot of optimization regarding the stars and how to make them fast. So now the idea is to build a virtual machine on top of the star system and see how we make it faster and efficient. But first, I will try to introduce to everyone what is a VM and how it gets proven. And then we can start doing some simplifications to see how it works, and hopefully move on to optimizations. For the record, I will be trying to explain tricks from many companies, including Starware, RISC-0, and Polygon, and that we also use in our same systems. So, we have two approaches for zero-knowledge proof. One is the ASIC approach, where each program gets compiled into one circuit. That's the usual case for snarks. Or we have the VM approach, where we have one circuit that can prove any program. That's what we usually call a VM. Examples of each of them is for ASIC approach. We have things like Synchron, Noir, Leo. From VMs, we have, I don't know, Cairo, Maiden, RISC-0, all the ZK EVMs, that kind of stuff. And we can further split VM depending on the arithmetic they use. Some VMs are using a finite field arithmetic as their basic element, for example, Cairo and Maiden. And some other VMs decide, like RISC-0, that maybe it's better to just prove any program, but just proving any program. Traditional program needs a binary arithmetic that is a little bit slower. Okay, another thing I wanted to mention is how many constraints are we talking about when we talk about the VM? Because we have this idea from ASIC programs that maybe we have millions of constraints or thousands of constraints. When we are talking about a VM made for finite fields, we are not talking about a lot of constraints. For example, the Cairo VM has around 40 constraints when we don't have built-ins, but I will talk about them later. And Maiden VM without chiplets has around 200 constraints, and the degrees are really low. Cairo VM has only degree 2 constraints. It has 1 degree 3 that gets reduced, and Maiden has at most degree 9. So how do we measure the complexity of a program? For ASIC ZK programs, we will talk about constraints, but for VMs, it usually makes more sense to speak about steps where each step is the execution of one instruction. Okay, so now that we have a general idea of both approaches, I will continue with VMs. So I wanted to show some generalization, some core parts that we usually have. So we usually have a lot of constraints regarding the CPU, like how each instruction should be executed and what are the valid next steps when we see an instruction. Usually, in all this system, we have a core part that is a range checker that is going to check that values are between a range. For example, we can check that the memory is between valid ranges that might be smaller than the size of the native field. We might have some constraints relating to the public memory, because if we are proving the correct execution of a VM, it's good, but then I can differentiate between a Fibonacci or a proof of the recursive proof or whatever. So we need to make sure not only that the VM was executed correctly, but that it executed the program that we want. And they usually have a mechanism to offload computation because they are not optimal for everything. That's usually done with additional constraints, and they might be really efficient to prove hashes or bit operations or whatever. But in that case, then it's like having different machines that needs to be communicated. So the communication has to be done. And there are many schemes for doing that. For example, shared memory, that is Star Wars approach with Cairo, with built-ins, or maybe a bus, that is Maiden approach with chiplets. So, this is already what I said. And now I'm going to show you a simplified version of how a trace that is going to be proven looks, and then we will go to the real one. So in the easy case, what we will have is each row of the trace is going to be one step of the execution, right? And then I'm going to see, okay, this is the state at step 0, state at step 1, state at step 2. And this works more or less, but in reality it's going to be a bit more complicated. In this case, one row is one step. In reality, this is Stone Prover or Cairo Prover from Star Wars trace, and we will see that one step is actually a lot of rows. So the analysis is a bit more complicated. Sometimes people stop and say, okay, we have this many columns, but it's kind of irrelevant because the layout might have multiple rows per step or whatever. And in general, this has the evolution of the virtual machine, but it has additional data. There is embedded data that might be a bit different. For example, you can see here that we have the sorted positions of all the memories that we are going to use to enforce some constraints, and this is totally not linked to the step. It shows the whole axis is to the memory in an order manner. Okay, and we will have another embedded data. For example, I told you that we need to prove the public memory. And the public memory, let's think that if we are executing a program and it has branches, we won't take all the paths of the program. So I won't have all the data.
You don't constrain the steps? Because I don't see the steps.
No, this is actually a step. The transition constraint.
The working is a step.
Yeah.
Okay.
The transition the transition constraint will be like two of these. Okay. This is state 0, for example, and then you will have another table that is going to be state 1, and you will have transition constraints. And for example, now let's go to the problem of the memory. The problem of the memory is a bit troublesome, because if you didn't take a path in your program, you will never see the actual access to the memory. Maybe some instruction is never reached, but you still need to make sure that that instruction was in the program. So, since that is not going to appear in the trace, we are going to have to embed it. And that is what is done in this column that is called the mempool. We will have some spare cells that we will use to place the public memory. And this is actually not the full trace, and I'm going to expand it now, because I'm telling you, here we have a mempool, and here we have a sorted mempool. So we actually need to use a protocol that is called RAP, Random Arbitrary Processing, to prove that one is a permutation of another one. that say that they have the same elements. So the trace is going to be extended with this. And this can have some caveats, particularly when working with small fields that Diego mentioned before, because there is some randomness involved on this, and if the field is too small, just one random field won't be enough to generate enough randomness for this protocol. So that's it. Well, now let's move on, because we are now going to merge many computers that do different things, make one that hopefully goes faster. So we are going to start writing coprocessors, and the idea here with building is to write many coprocessors or machines that will share memory with the CPU. And so in one way, there will be memory positions that will have additional constraints. For example, we will place some data in some memory positions, and we will say, okay, this position memory, they have all the constraints related to the memory, and additionally, it will have constraints that make sure that it's in a given range, for example, whatever. Or we could go with a chiplet approach that works a little bit different. In this case, we won't share memory, but the machines need to communicate anyways. So what we are going to do is try to use what is called a bus. So if you see each chiplet has its own trace, which is really nice. It's going to prove something, but it may not be related to the main CPU. So we need to make sure that the values that we hope to be constrained are actually used by the chiplet. So this is going through a bus, and the bus is a lookup argument. That is what Diego mentioned before. So this is wrong, but I'm going to show you a quick approximation of how this works. So we are going to do a cumulative product or a grand product, where each time that the M needs to communicate with the bus, it's going to multiply, do a product of all the data that should be in the bus, and when a chiplet processes the data, it's going to divide for the same values. So at the end of time, when we do the grand product, we should reach the initial state. This, of course, doesn't really work like that, because we are going to need some randomness that is going to be inserted via Shamir. Maybe we can use a smarter construction like lookup to make sure that this goes faster. Another nice trick that I like, that I really like, is continuations. There are two versions, one by Risirio and another one by Alan Shepeniek. So the idea will be the following. I told you that we want to prove an execution of a program, but we can actually split that program in parts and prove them independently. And this is going to be really useful, because we can parallelize the proving of one program in many parts, right? And one of the really good things about this is that we are no longer constrained by memory, because if we can split the program, we can always make a part small enough that the proving fits in the memory. So this is going to be really useful. And well, one part is really easy. You just prove each part of the program, and then you have to have a protocol to prove that the output, that the state at the end of a part is the same state as the beginning of the other part you are proving. There are many protocols. There are these two protocols to do that. And of course, this is going to look great with recursion, because if we can do an efficient recursion, and now we can split one step of the recursion in many machines, or on machines with not so much memory or not so much power, it can be really useful. Another trick that we have that might be useful for proving is bootloaders. It's a trick done by Star Wars. So we know that the cost of verification in Stark is logarithmic. So proving many small programs independently is much more costly than joining them all and proving them together. And we are going to join them not by recursion, but by using a program that is called a bootloader. The purpose of the bootloader is going to load all the programs in the memory of the VM, prove them all together, generate hashes that say, okay, I have loaded the following programs, and these are the results, and these are the hashes of the program I have loaded and executed. And then we prove that. And by proving that, we greatly reduce the cost of the proofs. Okay, so that was a quick overview of many tricks that we have to push this technology. I want to thank everyone that is building open source code for this, from which we are all able to learn. In particular, the three companies I have mentioned at the beginning. And of course, Fenbushi Capital and Lagrange, that is our company. Thank you very much, and if anybody wants to ask questions, feel free to do so.
Perhaps ask is if you could maybe elaborate a little bit on the so when at the beginning, like you presented how some VMs were based on fields, some VMs are based on like binary arithmetic.
Yeah.
If you could maybe elaborate a little bit on some of the trade-offs that exist between that space, because as you mentioned, like maybe risk reserve is like not that performant because it's like binary arithmetic based, but then like why did they choose that options, etc. Like could you elaborate on that?
Yeah, I'm sure that people actually reading this may have a better answer, but I will give you my take on this. So, definitely, when you do a VM for finite fields, you are free to optimize it for proving. It's something you have done just for this, so you will have little constraints, a few amount of constraints. It's designed for this. The basic operations are going to be on fields, not on bits. Working with bits is always more expensive because the proving system works with fields. It doesn't know about bits. That's a higher level abstraction, a bit. So when you're able to design everything from scratch, you can of course make it faster. But then you have to build the whole stack. You need a compiler, you need a language, you need absolutely everything. If you take another approach and say, okay, let's just try to prove RISC-V or prove something that already exists, you can leverage everything that you have. Now your VM is not designed for this, but on the other side, you have everything. You don't need to build nothing. It's everything widely used, and you just have to prove it.
And I guess following up on that, do you think that we will ever see a scenario where that ZK-VM based on binary arithmetic would provide, I guess, sufficiently fast performance such that the field-based ZK-VM wouldn't have that much of an advantage in that perspective?
I think they will have their niche. Probably, this is pure speculation, but I think if they can be good enough as to maybe make the others life a little bit harder. So probably you will see. Yes. At the beginning, it sounded a bit like an impossible task or like a really hard task, but we are seeing that it's not an impossible task and it's been done and they work really well. So they have an advantage. We will see how this ends.
I was going to say, do you see a world where we get VMs on client devices anytime soon?
Yes.
Like phones?
Yes. I think you can already do that. We run our prover in an ESP device that is much less powerful than your cell phone. That depends on what you are trying to prove. Probably you won't prove a recursion on your phone.
Yeah.
But the execution of a small program, I think you should be able to do it now.
All good? All right. I guess a round of applause for Mauro. Thank you very much.
Yeah, I think my talk is probably one of the only privacy talks today. I think Aztec will probably talk about privacy as well. And this is really reflective of a lot of the work in the ZK-SNARK space, a lot of it has been focused on succinctness and scaling and efficiency. And I think, so my background is I worked in the Zcash project for a while. And for me, one of the motivators for studying ZK-SNARKs has always been the privacy properties. So today we're going to explore programmable privacy on blockchains, not just limited to ZK-SNARKs, but exploring basically the whole design space of computations we can do over private data. So this is part of a project that I'm working on with Andrew Miller, Brian Gillespie, and Daniel Benarock, and we're going to write an SOK on programmable privacy. So I first want to motivate this problem with a very well-known situation we see in DeFi, which is the sandwich attack. I assume everyone's already familiar, so I will speed through it. But basically, a sandwich attack is caused by a privileged adversary having visibility into the orders coming into a certain block. And this adversary is privileged because they're able to reorder, insert, or remove transactions, and therefore cause the transaction to execute at a worse price. So one naive solution to this is, I think, done by osmosis. It's called the encrypted mempool. So instead of posting your transactions in the clear, you encrypt them to some threshold, and so the block producer is only working with ciphertext that look random, and the block producer has no strategy to reorder them. Now, the problem with this naive solution is that basically it's less efficient, economically speaking. There is no way to order your trades for a better execution price, firstly. And secondly, it actually also advantages those transactions that are commutative. In other words, transactions that don't depend on order and will execute successfully regardless of how they're ordered. And conversely, it puts at the disadvantage those transactions that need to come one after the other. Of course, this can be solved to varying extents by revealing some parts of your transaction. But yeah, in general, this sort of brings up the question of how we preserve trade privacy, but also still retain the ability to do meaningful computation over them. By the way, interrupt me at any time, because I'm not a DeFi expert at all. Yeah, and I've already had good conversations with people here who are like actual degens, and I'm always looking for you guys' opinions. So yeah, or a more general way to phrase this question is how we preserve the privacy of users' intent while still ensuring that they're executed faithfully. Now, yeah, so I motivated this topic with the sandwich attacks, and I'm gonna just stick to this example. I'm going to basically explore this topic using just one application, which is the limit order auction. And yeah, we think that this application is general enough that it gives us an overview of all the primitives needed for a truly general application. So once again, I'm pretty sure you guys know what limit order auctions are. So I will also speed through this. But yeah, basically, a limit order is an order is an order with a fixed input of a certain asset that you intend to sell. So we fix the input asset and we fix the amount that we're willing to sell. And then we also specify the asset that we're trying to buy, as well as the amount that we're trying to buy. So in the case of an order book, we can specify all of these fields. And yeah, basically we are willing to execute this order if we can get at least this amount or more. So the buy value here is specifying the price, the limit price of our order. So that's in the context of an order book. And in the context of an automated market maker, we actually cannot specify our price. We cannot specify the value that we want to buy. Instead, this value is publicly determined by the amount of liquidity available. But we can specify a slippage, so that beyond a certain delta from the public price, we refuse to execute the order. So cow swap is a very good example to look at here because they make use of both the order book and the AMM. So what cow swap does is it takes in a bunch of individual trades and it batches them. And then it can share liquidity for all the trades in one batch. And it looks both in its order book and in the on-chain AMM. So now that we are familiar with our motivating application, the other sort of introductory piece that we have to go through is cryptographic primitives. So I'm pretty sure everyone already knows all of this, and what's new here is basically a framework to compare these primitives. So I think of them as like split into two classes. The first is private verification, and the next is private computation. So anything you do with zero knowledge proofs falls into private computation, in the sense that the computation all happens prover side directly on the private witness. And the zero knowledge proof can only be verified and shown to be valid or not. So no further computation is done on the zero knowledge proof. Whereas private computation requires some sort of encryption that preserves some structure of the original data, such that a third party can perform meaningful computation on the ciphertext blindly. So yeah, to get a little finer grained for private computation, the simple case I described just now directly maps onto the TEE. So the TEE, you literally just encrypt it to the key inside the secure hardware, and they decrypt it inside and perform a computation in the clear, and then re-encrypt the result. Whereas threshold private computation is the same shape, but you're replacing the trust model of secure hardware with a threshold guarantee. So basically, a quorum of these parties, if they collude, can decrypt your ciphertext. But if everyone's honest, then what they do is they work together to compute some joint program on your secret shared plaintext. Okay, any questions? Yeah, this is all really high level so far.
Oh
yeah.
This one.
What?
The threshold compute and TEE, right?
Yeah.
Most of the things which you mentioned here, there's kind of a trade-off. The solutions, the cow swap and intent and everything. They have a centralized RFQ and then some sort of a solver kind of thing. Especially like, cow swap is great to a certain extent, but you still don't have privacy or something like that there. But what I'm mostly interested is like you mentioned about threshold compute. If you take it from an MPC perspective, T is like it never worked. It's kind of an alibi, that plausible deniability that we don't see, but you always see it. Sorry, that's my bias.
Okay.
But MPC solution is like, is it possible that could you have a credible commitment can be done for this kind of limit order book? Because even if you have privacy, there are a lot of other things you can do it, like the auctions that you mentioned, like you can escalate the price, but you still have the participants that are like mostly centralized or preferred and things like that. So you have a lot of analysis you can do, and you can do a lot of attacks. But what I'm most interested in is like the critical commitment devices combined with the threshold computation. You can have some sort of a temporal rule that if an attack is coming, if the privacy is leaked, then the actor can be kicked out from the game.
So sorry, if the privacy is leaked, then what?
Yeah, let me tell you a different way this one. So you pay in the trades, in the game theory, you basically pay for something to get a trade, right? So let's say you pay $100 to get an ETH, something like that, but the game will shift over the course of time, then you will start to pay not to get excluded from it. Right? So, because you have more data, and most of this trade will actually going to get posted in a blockchain ledger. So, how do you get this kind of the game theory going on parallel with the privacy? Because we're talking about there's always leakage afterwards.
Yeah. So that's a really good question. I think oftentimes it is a trade-off between privacy and efficiency of your trade execution. So we're going to go into a few implementations of limit order auctions later on, but one that I can think of off the top of my head is a protocol called Renegade Phi. So Renegade Phi is an on-chain dark pool, and by default all your trades are dark, like they're completely concealed. But the problem with that is that if your trade is completely dark, all you can do really is to sit and wait for it to be organically fulfilled. So Renegade Phi provides this option for you to light up certain parts of your trade, like the asset pair, or like or maybe the price or the amount, and this can motivate a counterparty to fill your order. So yeah, I think the design space is huge, and yeah, but I do think that the question of like what kinds of users will be attracted to what kinds of privacy is a very interesting one. So I was talking with someone yesterday who made a good case that the users who care most about privacy are those the most toxic users, like the whales who are trying to dump. Yeah, that could very well be the case as well. So it's definitely an
So
interesting
it's
design.
more ephemeral, that's what you're saying.
It's more ephemeral.
Like, if you want to do an oversized trade or something, most malicious, or I would say toxic users, they want to move sizes, then they want some privacy. Or if you want to do some sort of an airdrop or...
Yeah, exactly. Exactly.
I think a better term would be more informed.
More sophisticated.
Yeah, that's great. Thank you.
More informed, okay. Not more toxic, okay. Cool. Yeah, but that was a good preview into the next part of our talk, because yeah, we're gonna go into some implementations of limit order auctions. But as a side note, I wanted to mention about primitives is that, yeah, oftentimes they're stacked. Oftentimes, for example, zero knowledge proofs are necessary in any scheme that depends on FAG to prove that your ciphertexts are a meaningful encryption of some real data, not just trash. Also, these primitives could be stacked for defense and depth, so I know TEEs are like suspicious. But in a threshold encryption scheme, you could put each key share in a TEE, and that would be better than like having it on like your a Word document. So yeah, that was just a side note. And now we'll move into, I think, the meat of this talk, which is the actual implementations. So yeah, we're gonna look at 2 order books and 2 AMMs. So, and this is the framework that we're gonna use. So we're gonna progress through 3 phases of computation. And these phases could take place off-chain or on-chain. So let's just go into the first example and you'll see. So the first example, no, I'm gonna skip this one. The first example is Zaxi. So how many people here have heard of Zaxi? Yeah, cool. So Zaxi is basically a blockchain that allows users to verify arbitrary programs. You can make a program, make a verification key, upload it to the Zaxi directory, and then, yeah, just like create and destroy records according to your own verification key. So, given this, how we would implement an order book or a swap is that we would enforce some validity predicates on the notes created and destroyed, or created and consumed in that transaction. So some important invariants include that the value is preserved, and it includes that the asset IDs are swapped. And it also includes that the owners of the output notes are swapped. So I think I went over this in a hand-wavy way, but this is the least interesting example, and you'll see why. So, yeah, in phase 1, in phase 1 of Zaxi, both your maker and taker, they independently create a proof for a spend of their note. So this is the note that they're intending to trade, and they prove that they have spent this note. So the point of phase 1 is that you can do it independently without help from anyone else. Now, in phase 2 is when they actually need to discover the counterparty. So they need to be made aware that there's actually a fulfilling order on the other side. And how Zaxi implements this in their paper, they call this a closed order book. And yeah, it's not very interesting because all it involves is both parties revealing their trades to a centralized off-chain order book operator. And this order book operator matches these trades and creates the output proofs. So why this is better than just a normal centralized operator is that because the order book operator has to create valid output proofs with these that fulfill these validity predicates, they're not able to mismanage your funds, and they can only spend them. They can spend them only if you find a truly matching counterparty. And so this order book operator creates a completed transaction that balances out and submits it on chain, along with the all the spend and output proofs. Okay, this example is easy, right? Yeah, so like we said, there's no privacy from the order book operator, and the question here is this okay? So, yeah, and the answer is it depends on your use case. So, a lot of, I think a lot of trading, whether on-chain or off-chain, already now goes through a trusted intermediary. And if I'm, for example, a whale, and I want to make an iceberg order, that is like I have a huge cell, and I want to cut it up into little cells, and I don't want anyone to know that they were all made by me. So if I trust an order book operator to not reveal this, then I can still execute all my little cells at a good price, because this order book operator doesn't reveal them on chain. So yeah, from the perspective of the whale, like they still got a good execution. So this was totally okay. So yeah, but of course this order book operator could front run. So I have it in text what I just said, but I won't bore you with this. I'll put the slides somewhere. The next example of order books is pretty similar. So this is implemented in something called Taiga, which is part of the Anoma protocol. So it is pretty similar, but it's just phrased differently. It's phrased in terms of intent. So the maker and taker, once again, they each spend their note, and they encode the desired outcome of their trade in an intent note. And this intent note is sent to an off-chain solver. So if the solver sees a match in intent, they can consume, oh, this is a typo here. This should say tape. Oh, and I can't edit it, right, because this is not my computer. But yeah, so the solver matches and consumes intents to create, once again, the corresponding outputs. And now the transaction, the balanced transaction, consists of these three partial transactions. Yeah, so it's similar to Zexi, but I think Anoma or Taiga, really what they've done is make the intent of first-class citizen in their protocol. And so, yeah, they're expressing their applications in an intent-centric way. But if you wanted to implement this in Zexi, you could. So those were the two, oh yeah, here's what I said in words. And those are the two order book implementations. Are there any questions? If not, we'll move on to AMM.
Sorry.
Yeah.
I had a quick question. So I think the order book model that you have looked at so far was, well, besides the Anoma one, maybe a bit more exception, I guess, but with the ZKXC one, let's say that order book was, is it managed off-chain?
Yeah.
It is managed off-chain. So I was wondering, like, how would it look like, let's say, if the order book was managed on-chain in some sort of like a binary tree type of a fashion?
Okay. So I guess like we would put commitments to our orders on-chain, and then arrange them in like in a binary tree structure. I don't see a way to do that doesn't just reveal the order, because, well, unless like we assume that we committed to like some threshold who is able to compare like greater than on the orders. And this is, yeah, so this introduces the threshold committee, which Zexi doesn't have. Yeah. So I think the point here is that in ZC, because they only use verifiable computation. Sorry, they only use zero knowledge proofs that don't allow further computation on the proofs. Yeah.
Could you do it peer-to-peer and avoid the one in the middle?
So instead of going through a centralized operator, could we maybe send, like gossip these orders, for example? So sort of the desired privacy guarantee here is that we only leak our order to the person who successfully matches it. And so if I gossip my order to everyone, then I might as well send it to the public mempool. Yeah.
Yeah, makes sense. Thank you.
But if you wanted to decentralize the operator, you could replace it with a threshold. And I think that's what Renegade Phi does. Yeah. So by the way, this off-chain solver is like, this is Suave right now, except they don't need to make validity proofs, and they can do whatever they want. Yeah. But they wanted to put it in a TEE, but I don't think they have done it yet.
I just talked out. Could you make quite clear for me the difference between Zexi and Taiga? Because it seems to me that you mentioned intents are first-class citizens, and that was the only real thing that I could hold on to that seemed different from the two. So can you just make that clear for me? And it's a solver instead of like a centralized.
I don't think there's a difference.
Okay.
Yeah.
But the intents are partial orders, right? Unlike the AMMs, even in Taiga, their orders like constrain partial orders in terms of the normal language.
Yes, but
how do
yeah.
you find this kind of balance between privacy and counterparty discovery on a fair market principle?
Can you repeat that last part?
How do you get the counterparty discovery if you want to have privacy? If the intent is a partial order, and the counterparty should have some sort of incentive to satisfy that, so it's not an AMM, it's just on an open state or something.
So yeah, if you know the intent, you know the order. And so the intents here are submitted to a trusted solver.
Yeah.
Yeah. And so it's private to the blockchain, but it's not private from the solver.
Okay, thank you.
Yeah. So now we'll move on to some AMM constructions. So the most straightforward one is secret network. So how secret network works is that each of its consensus nodes is a TEE. And each of the nodes, unfortunately, holds this consensus seed inside it. So there was that attack, SGX fail, that proved that you could exfiltrate the consensus seed of the whole secret network from the TEE. But anyway, this is not like a fundamental flaw in TEE-based blockchains. This was secret network's flaw. So how you would, so yeah, there's an app secret swap on secret network. And how it works is that, so it's an AMM, which means that the liquidity positions are all public. So the user can publicly pick an optimal route for their trade. So the user then encrypts their trade and the route to the consensus seed and submits it to one of the consensus nodes. And then, yeah, this is decrypted inside the TEE and executed. And the updated state is re-encrypted. That's super easy. And by the way, how the secret network consensus works is that every other validator also it's like in the EVM. They also run the same transaction and convince themselves that they end up with the same state.
Could you run, like, could you do what Suave does on secret network? You know, just run an arbitrary compute if it's been deployed on the TE, so that the inputs are kept secret. But you run jobs like block building, for example.
Yeah.
So it's like Suave is the
You could run a solver. Yeah, that's Suave.
Okay.
Yeah. But what the difference between secret network and Suave is that secret network has a whole network of these TE nodes, that are staked. So, sort of a more interesting AMM is Penumbra, and Penumbra is more interesting because it uses batch swaps. Now, for secret network, by the way, by just observing, okay, I tried out secret swap before this talk, and then I went to look for my trade on the block explorer, and then I realized that every block in secret network had only one transaction. So, if you look at the public prices before this block and after this block, you can reverse engineer exactly what happened in that block since there was only one transaction. Yeah, so really what this says is secret network only works if there's many transactions in the block. Or another way of saying this is that it only works if there's the swaps could plausibly be part of a batch. So basically in an AMM, in order to preserve the privacy of individual trades, we need to batch the trades. Otherwise, sequentially executing each individual trade would precisely allow us to reverse engineer them. So what Penumbra does is batch swaps. And so how it works is, first of all, each user, once again, they privately spend the node that they intend to trade. But here, there's an additional step where they encrypt the spend to Penumbra's threshold. And so the guarantee of the threshold is that only a quorum of them working together could decrypt any of these ciphertexts. And so our assumption is that a quorum of the Penumbra threshold will not collude, that we cannot get this quorum. So now, individually, these validators can add up the encrypted spends because they were additively homomorphically encrypted. So individually, each validator can blindly add them up. And by the way, it doesn't matter what order they add them in, it's commutative. And so the validators reach some encrypted batch spend, and they work together to decrypt that batch spend. And this batch spend is now publicly decrypted and publicly traded on the AMM against the liquidity pool. And then later on, what the users need to do is they need to claim their share of the output. And how they do this is they prove the knowledge of the preimage of some input that was involved in the batch swap. I will let this sink in. It's a cool design. They call this primitive flow encryption. So, yeah. So once again, your anonymity set is the number of swaps in the batch. And if your batch has one swap, you get no anonymity. Yeah. And yeah, your goal as a trader is to preserve your long-term strategy. So since each of these spends and outputs is like a node commitment on Zcash. So it's a third party doesn't know the individual values committed to inside these spends and outputs. So yeah, and a third party cannot link spends and outputs by the same person across different batches. Any questions?
Is there any time constraints? Like, is it happening like every 30 seconds or a minute for batches?
Yeah, I think that's a good question. Yeah, I think, Penumbra has a block time. And so the point of the batch swap is that it happens at the same granularity as the block production. And this is as opposed to in Ethereum, where individual swaps are at a finer granularity than the block. And that's the problem. Like, that's what causes MEV, is that you can reorder trades inside a block. So yeah, the batch executes as frequently as a block is proposed.
Actually,
the bigger the batch, the better the privacy.
That's true. If we waited longer, we would get more privacy. That is true. And the trade-off is like, for example, if I like the price now, I would rather trade now with less privacy, maybe.
The block time in this case wouldn't matter too much, right? Because it's just, I mean, I could arbitrarily set a parameter to say that Penumbra wanna accumulate, let's say, 1,000 transactions, and if it doesn't reach that batch scale, then it just simply doesn't go on chain, for example.
Maybe, yeah, maybe. But once again, that's a trade-off because as a trader, like, I don't have this guarantee that my trade will execute within a certain time, and it could have slipped like a lot in the interim.
You could also look at the silver secondary markets, the price of one gold. Like, you know, if you're trading like in a bigger sizes on the same highly demand assets, you still know the prices where it moves. But it's still a really good design. It's amazing.
Yeah.
But if a group of actors start like spamming the blockchain with a transaction, they can reduce the anonymity set of everyone else, right? And try to recover the information.
Yeah, definitely. Like, or if, you could fill up like every trading pair with swaps that like are your own and are like totally meaningless. And then you go and observe the public price change, and you know, like, okay, like none of that was caused by your garbage trades, right? So it must have been caused by like the only trade that wasn't yours. Yeah.
Okay, thanks.
Isn't the only thing you're getting here anonymity? You're not getting like privacy of the trade price?
So, okay, yeah, there is no privacy of the trade price because the price is public in an AMM. But what is private is the amount sold in each of these orders. Since they're executed as a batch, you don't know how much of the batch was like contained in the first swap or the second swap. That's why the larger the batch, the better your privacy.
Is there any difference between someone doing a penumbra style thing here and, let's say, what Railgun's doing on L1 or Aztec connected, just having an anonymous shielded tool that's interacting with the public ARM?
Yeah, so Railgun, Nocturne is also doing something similar, I think. And what they do is they allow arbitrary transactions from an anonymity set. And so it's, I think, so look, if I spent from if I made a trade on Uniswap and I spent it from like the Nocturne shielded pool, this trade is made in the clear, right? And so this trade is completely non-confidential, but it is fully anonymous because anyone in the Nocturne pool could have done it. So yeah, in that case, that you only get anonymity and you don't get the privacy from this batch. Yeah.
Got it. Thanks.
Yeah. So the batch swap, yeah, it allows you to conceal your long-term strategy. Like people can't identify multiple orders that look similar, for example. Am I out of time? Okay. So that was all my slides, and I wanted to do a little discussion, but we can do that after, like at the end of the night. Thank you.
Thank you very much. Today we're going to be talking about proven decentralization and specifically how we approach it and certain design considerations that need to be taken into account. So I'm not going to bore with the whole roll-up is how do you define a roll-up, because I think most of you guys here, if you want to, I can, Joe, if you're interested, I can. Yeah, I'm not going to bore with that, so let's assume we know what a rollup is. There are two types of rollup, optimistic rollup, ZK rollups. We're talking about ZK rollups now. And in case there's anyone from Starkware here, when I'm saying ZK rollup, it's what you think of when you say validity rollup. It's the same thing, just in case, because Starkware people get confused by the word ZK rollup. And by default, ZK rollups have two roles, explicit roles. One is the prover, who is responsible for computing the validity proofs, and then the sequencer, which is responsible for ordering the transactions and basically proposing preliminary sequences of transactions that are then finalized by the base layer. And of course, the rollup communicates with the L1, which means that we have a bridge on the L1 that ensures that the validity proof is verified and also the data is correct. Viso is going to explain a bit about this, the building blocks of Scroll, how it is right now, and then we're going to go into the details about the design considerations.
Yeah, so basically the current Scroll system is completely centralized as it is right now, and it basically has two fundamental components. So basically the sequencer, which takes input from users, and these are transactions, and it's responsible for basically producing an ordered block of transactions that are executable. And the output is blocks, which may be aggregated into chunks if there are not enough transactions to fit the circuit capacity within the block. So the next part is the prover, which basically takes as input the block and computes a ZK proof that proves the validity of the execution. And it does this for every block or chunk until we have enough of those to fill a bus, which is basically the final unit in the Scroll system, which is basically aggregates all the proofs for the individual components, the blocks or chunks. if you like. And this, again, like a zero-knowledge proof that aggregates all the other proofs that are completed. And this is what gets submitted, to L1 for finalization, which verifies the proof and basically updates the statements, etc. And basically this is the completion of the execution. So, is this one the commit version?
Yeah.
Right, let's move down a little bit. So the really big component, the important component here, what we're dealing here with is basically the scroll proof. This is the most fundamental component. Without a prover, there is no system.
We can see your shape.
Okay. Yeah, that's without a prover you cannot see the system. But the prover has some constraints, right? It's really expensive hardware. You need like a beefy GPU. And the proof, currently takes quite a bit of time. Practically takes like 15-20 minutes to compute. There is active research on basically reducing the proof time and also increasing the server capacity. But it's still a little bit ways off. So, given that, the provers are obviously the scaling factor, the scaling limit. So you can only scale the system with the number of provers that you have. Because even if you could cram, thousands of transactions, Solana style, within a block, you still need to be able to prove this block on time. And basically, as you produce more and more blocks, you need more and more provers, so that basically you can keep your pipeline full. So if we do back of the envelope calculation, this is my favorite types of calculation. So let's think about this. So if you have a 3-second block time, which is the current block time in Scroll, okay, that means within a 20-minute period, which is how long it takes to compute a single proof, we're going to need at least 400 live proving hardware units. So, and if you want to add some fault tolerance, because sometimes these units fail, and you need a fallback, and timeouts and everything, so you need to double that. And if you start thinking about, okay, we have low transaction volume now, we have 3 seconds block time, what happens if we have high transaction volume as we hope we will have today? And basically we make a block time 1 second, then that means you need, thousands of provers. So, yes?
What throughputs are assuming in the 3 seconds?
In the 3 seconds, so currently numerical blocks are pretty small, but we're going to increase that. So, if you go down to, with high volume, and you have 1 second block, it's feasible to have eventually, 1,000 transactions per block. So, it's a pretty decent DPS, but the thing is that you need the hardware to drive it, right? Okay, so this is where the impetus is coming for decentralized provers, right? It's pretty obvious.
So there are a few reasons why we would like to decentralize the prover. So one, it just makes sense to decrease the probability of something just completely failing and therefore resulting in a liveness failure. Because if you have a decentralized prover network, then let's say if one prover fails, it's okay to fail over to another one, and it's fun. And then also another thing to consider are operating costs. So you have, for example, a bunch of former ETH miners, shout out to them, that have their hardware just lying around doing nothing. And that hardware is pretty useful for us, for example. You could hook up a rig and compute proofs. Whereas if we were doing it ourselves, we would either have to either have to rent all the hardware or buy the hardware and build the rigs ourselves, which means that there's a lot of upfront cost, even assuming that we somehow solve the problem with decentralization. And obviously we are building blockchains here, and one of the primary, I don't want to say selling points, but more like one of the benefits of blockchains is that they can be not trivially, but they can be easily decentralized, and I think a centralized blockchain just doesn't make sense. Just use AWS. What's the point of a blockchain? So it's kind of part of the core ethos of what blockchains are about, and therefore it just doesn't make sense to build a system that is centralized, even if you ignore everything else. But of course, there are technical reasons why decentralization makes sense.
So, given what the rules say, basically we can do why decentralize the provers. So basically, we want to create a certain network where the costs are shared and the rewards are shared. And basically this creates alignment with the values of the Ethereum community. You know, like it builds mindshare, and you know, like basically it's a must-do move. We cannot afford to not do it, because otherwise, what's to differentiate us from Solana? Why are we even Ethereum? Right?
I'm not signing off on this, by the way.
Right, so basically the pillars of decentralization is all the three things that need to align. You know, there is protocol, there is economics, and there is governance. Okay, so you know, here we are, right now we're in the phase where we are designing the protocol with input, you know, like on how the economics are going to shape the protocol, because you cannot design one without the other. And governance is something that, as the system gets decentralized, it must come in, because you're not the owner of the network anymore. So you know, there has to be some governance structure, but this is something that can come in the form of a DAO or specifics of the L1 contract. But this is something that can come slightly later when eventually we have a token. So, with that, how do you decentralize the provers? Okay, Toghrul, do you want to take us through?
Yeah. Is it working? Yeah, it is working. Yeah, I think one of the main goals that we were going for, even initially when we were thinking of how to design provers, is to make it permissionless. And also, L1 staking here doesn't mean that, we assume that there is some way to have simple resistance. In this case, assume there is ETH token, but you can also do it with proof, POA, etc. There are multiple ways you can do it. So that was the core pillar of what we're trying to do, is to have a permissionless prover network. And on top of that, we also understood that we needed quite a lot of provers. So we understood that the prover set has to be quite big, as Viso explained before. Even like in the very, very, very optimistic scenario, you would need hundreds of provers, and if you crank the throughput up, you might even need thousands of provers, which is not such an easy task. So currently, the design that we were going for initially, we had a sequencer that was computing blocks, proposing them, and then basically assigning provers, or like deterministically getting provers assigned to each block, and then those provers computing the proofs and submitting them asynchronously. Let's say if the prover failed to submit the proof within a certain period of time, then we could just elect a fallback prover, and that prover would submit the proof instead. Viso, you were going to go into the details, or you?
Yes. So basically, the main idea here is that you start with a VRF. It doesn't have to be an external network or something particularly complicated. It just needs to be something that provides consistent deterministic randomness. Well, okay, this is an oxymoron. Basically, consistent randomness that can be deterministically verified by everyone. And this you can do with pre-rando. You don't need anything particularly complicated. Now, given a random seed, okay, and the set of participants, which brings us back to, this has to be known at L1, then everyone can compute the same order, basically, by using a PRNG. You don't need anything particularly complicated, just a permutative congruence generator will do, but what you need is good statistical properties so that, the output is uniform. Given that, then all participants compute the same schedule, and you know who the next prover is for each particular slot for this particular block, and who is the aggregator for this batch. So this is a nice and simple design. It does have some issues, however. The first thing is that you have to fix the rewards to happen at L1. So you fix the rewards and everybody gets the same reward, okay? That's a governance issue, and it's also not particularly efficient because you don't know whether these rewards have anything to do with the actual market cost of what we're computing. On the other hand, okay, this is a very, very, very fair system. There's no way to have a centralizing force that can monopolize the proofs. And the fact that the rewards are known, it means that you can have a stable income and you can do your planning on that. So, of course, that's not the only approach, and it also has one other disadvantage, because basically once you've settled on your prover set, what's the incentive to improve my prover? Why should I make 30 proof times priority or anything like that? So basically can lead to stagnation of technology, which is not a very good property to have. So given that, there's also an alternative approach how you can do it. So you can do it with an auction mechanism. So again, given the set of provers, and you have a block produced or a VAT, then like you forward the block into the network, and the provers bid how much they want to be rewarded in order to produce a proof. So this is in a sense a tender because it's not highest bidder, it's lowest bidder, so it's a tender that they're bidding for. And it has the advantage that it's completely market driven. It's market forces, it's capitalism versus communism, if you like, but it has some problems, right? So there is auction protocol complexity because you need to design an auction protocol that is fair, so that basically you can be front running. You can't just have a central trusted entity to submit the bids because then the central trusted entity would front run to you and have its own hardware that submit a lower bid. And the other problem is that there are serious concerns about basically centralizing forces. So you get the fastest proven technology, then you can potentially monopolize the proper market. So that's the disadvantage case, but we believe that there are solutions there, and we're actively working on that. Oh, you have one.
I think before we go there, there are also a few things to add. That also should be part of the consideration about how to design provers is a lot of people, when they think about provers, they think, oh yeah, you can just emulate proof of work, like do something like what Bitcoin does and just have a bunch of provers compete with one another. But the difference between using this approach with in proof of work and in proofs, there are a few differences. So one, it's not a difference, it still applies to proof of work. It's inefficient, it leads to a lot of waste of resources. It's not really necessary in this case. But the main concern is it's very centralizing because in Bitcoin there's randomness involved, inherent randomness involved in the process of proof of how you select the leader. And so essentially you can think of your probability of winning at a given round, assuming all the other conditions are fair, so the network is synchronous, etc., is roughly equivalent to your percentage of the hash rate in the network. Whereas in here, it's likely that the most efficient prover is always going to win, which means that long term you end up with a scenario where the most efficient prover always wins. And is that a good thing? Because you end up essentially with the centralized prover, and instead of having that, you might as well just run a centralized prover yourselves. There's no difference here. And thirdly is, no, that's it. Actually, sorry. And then another thing that we have been actively considering lately, and we think that it's the right approach, and I actually gave a talk about it at another event today, is we actually don't really need sequencers as an explicit role. So think of it this way: if you have a protocol that has a decentralized sequencer and a decentralized prover, so you have a bunch of sequencers, let's say a few hundred, and then a few hundred provers as well. The sequencers are likely to outsource the block construction to some specialized builders, the same way Ethereum works. So what do you end up with? You end up with a system where essentially sequencers are the middlemen between the provers and the builders. So why not just remove the sequencers, give the pre-confirmation rights essentially to the provers, and just have them run the whole thing and just outsource block building? Because at the end of the day, it makes no difference from the protocol perspective, from the security perspective, but at the same time, you leak less value and incentive balancing. It becomes much easier because assume that you want to distribute the incentives correctly between the provers and the sequencers by default. Think of it this way: because sequencers have the privilege of ordering the transactions, they get to keep all the MEV profits by default if you don't enforce any low incentive balancing. And therefore, and it's likely that MEV is going to be it's going to make up a significant percentage of the value accrued by the network.
which means that there are less incentives of being a prover than being a sequencer. And we actually need more provers than we need sequencers, because even if you have like 20, 30 sequencers, that's perfectly fine. We don't actually need that many. And yeah, and you could solve it by adopting PBS or like a variation of PBS. But then the problem is, if you assume a scenario in which the sequencers outsource the sequencing rights to the builders, which is likely to happen in a decentralized scenario, then you essentially end up with a model that has PBS inside PBS, which means that first, you introduce additional complexity that isn't necessary, and two, as I said before, it leaks value. And so we have been recently for like a few months working in the direction of completely deprecating the sequencers and just basically giving the sequencing rights to the builders and building the optioning model between the builders and the provers, so the provers run the consensus in the network and are responsible for reconfirmations for the users.
Yeah, and this is pretty much where we are. We've been churning through designs internally, and we're now ready to start talking about them. But then, hence this presentation. Just give me 1 second. But basically, we would like the community input here, because we want this to become more of a community project. And we would like to hear critique about both approaches, so that we can move forward. And the nice thing is that we don't have to build a fully decentralized system in one go, right? We don't have to start with both decentralized builders and decentralized provers. What really matters right now is that we get to decentralized provers, and we can do this initially with a centralized builder. That's not a problem. And later we can even decide to adopt, for example, based rollups, so based sequencers, which is something that the Ethereum has been, or not. I was going to say that, but we just don't know. This is probably 5 years away, so maybe in 5 years we decide to adopt it. So there's nothing stopping from doing that. But the important part is going to have a decentralized market for provers and a market that's efficient and fair. So.
Oh, I think one last thing that I also wanted to address, because we get a lot of questions about it, and I think you guys also probably get it quite a few times, is what about prover markets? Like, do you want to support prover markets or not? And we, at least we thought about it a bit, and we think we're going to build a system that is agnostic to how you compute the proof. So essentially, think of how Ethereum works. Ethereum is agnostic to how the staking happens, whether you stake and run the full node yourself in the validator, or you give it to Lido. And we think we're going to take a similar approach, where you can either run the prover yourself, or outsource it to somebody else, etc., etc. And yeah, and just let the market forces figure it out, because at the end of the day, in our case, having, let's say, a Lido-like entity on Scroll doesn't really impact the security that much. The worst thing that can happen, your proofs get delayed by like a few minutes, which is not that big of a deal. Whereas in Ethereum, Lido can actually cause a lot more problems. So yeah, so we don't think something like Lido emerging on Scroll is a worry, and therefore we're just building the system that is completely agnostic to how the provers, how the provers actually get to produce the proofs. And one more point is, hopefully by the time we get to release this stuff, Viso and I commit to the fact that our blog posts, etc., are going to look a bit nicer than
absolutely. The non-slides.
I'm going to make sure that anything that comes out from Scroll is a bit nicer than this.
So, we had a question?
Yeah, so actually I have a background in MEV, so I'm quite interested in proving markets. I think you're going to hear more about prover extractable value. And so one interesting thing, and I agree with the sequencer logic, is that there could be vertical integration between the block builder and the provers, because kind of the receipt to become a good builder is to be quite efficient in your compute is the same on the prover side. And the other thing is, if you're a builder, you can kind of front load the proving job, so it gives you an inherent advantage. But I also agree that the sequencer it could be a blocker, but it's kind of an inefficient blocker. But I don't know what's your take on that.
funnily enough, when I joined Scroll in late 2021, that was the first thing that I brought up, like this similar point. So we basically went a whole circle and just came back there. Yeah, to some degree, builders, the roles are not similar in a sense that they perform similar roles, but the requirements are similar, that you want to maximize the performance and extract as much as possible from your hardware. So I think it's possible that builders would be running provers. The only thing is that with provers, we actually need a lot of provers, whereas with builders, it's likely that it's quite a centralizing force here, so you're going to end up with a handful of dominant builders that are participating in the network. So I'm not sure if there are enough incentives for them to run a large number of provers, but like just running one prover won't make a difference for a builder, so I don't see why they would do that.
Another point I'd like to make is that like running a builder is like running a service, right? It's a user-facing service that has like certain difficulties in running. It's not something you can run at your home. So like that's yet another reason to basically make sure that we have professionally run builders that basically are highly efficient and provide a good user service, which is not something everyone can do. And at the same time, the builders are shielding the rest of the network from all the user traffic. So they play a very important role, and it's absolutely fine if we end up with just a handful of them running hand cloud, for example.
As long as but the only thing is, with that we need to somehow try to enforce real-time censorship resistance, because like otherwise you'll have to rely on forced inclusion, which can take hours, so it's not nice. And we actually have working ideas on that, and we're actively working on that as well.
Hi. Sorry, I have a quick question. Hello. Hello. Could you quickly go back to the VR part?
It's played out on the mic.
Yeah.
You can see when someone is a Linux user straight away. Yes.
Yeah, so as far as I understand, you have these pseudo-random selections based on VRC, and provers are all like just permissionless set of prover pools, and you kind of like set it out that, right?
Yes, so basically think about it, you get from L1 the list of provers, right? They're known. This is why there was a mention about staking, so somehow they need to appear on L1. So basically, even from L1 pre-rando, okay, and possibly a transformation of it so that it applies for the next n epochs, okay, so you come up with a seed. So basically you sort the provers, you generate a pseudo-random number given this random seed, and then basically you just create a CDF and then you select the one that falls in there.
And are they staking, or are they just like...
It doesn't have to be staking, you can take different approaches here.
Well, what's the approach?
For example, you can make you basically compute a certain amount of proofs that are required to be submitted to the L1 to be eligible to be an L2 prover. There are a few ways you can have Sybil resistance. It doesn't have to be staking, but I think using something like ETH as staking makes sense here.
Right.
Yeah, it's also very simple. So
yeah,
not restaking though.
That's
a completely different topic.
I guess, yeah, I think one thing I was trying to understand better was like, what would be the cost of bribing in terms of if you have, let's say, I don't know, for whatever reason it might be, perhaps that at a certain slot in the future time, you know that the prover is XYZ consecutively, and that you know that perhaps some tokens are launching XYZ consecutively, but maybe perhaps you are the sequencers for the Y slot, XYZY. So you may have some incentive to censor all of the prover XYZ such that you can accumulate all of the MEV all the way back to the Y.
But censor the prover in terms of
not letting them to submit this.
To submit proofs, or
yes, not submit proofs.
So basically, but that doesn't make a difference because your blocks are already, so your data availability is already on L1. So the only thing that you do is you churn through the provers. And
it's the latency.
Yeah, it's the latency. So the only thing you achieve is you delay on chain finality. That's the only thing that you
But
can
but
achieve.
could there be a time in which you can actually like achieve some sort of reorgs within the L2s?
So the current line of thinking that we're gonna adopt hot stuff too, and run hot stuff too.
So basically, logs dynamic. So basically, our difference is that we're going to use broadcast instead of point-to-point links.
Oh,
Yes.
so you're gonna have hot stuff too to achieve some sort of pre-confirmation?
Yeah.
Oh,
So you're gonna have strong economic
Gotcha.
confirmation, and then you put
Right.
the data on the L1, and then you get actual finality.
Right. Because without it, then you could say that whatever sequencers at Y that is like blocking out all of the.
Yeah.
Right. Okay, that makes sense.
Okay, and like this is also one of the another disadvantage that you have with the L1 generated schedule is that basically you have to protect the IP address of the provers in a sense, because this is also a problem that exists in the Ethereum core network, in the validator network. Because like if someone knew the prover, so you could basically launch a DDoS attack to knock it offline if you knew the IP address. So this is one extra difficulty, which is harder to pull off, like with an auction mechanism, because then like you don't know in advance who the prover is going to be. So you're going to have to launch an internal sales attack against the entire network.
So you can tell that Beezer is a networking guy based on how much concern he has about IP leaks. I don't. Joe, I think you had a question.
Oh, I forgot it.
There's a maybe each other or
just pass it.
So it's my understanding that you guys break up like chunks and blocks are the same thing, right? And then a batch is a bunch of chunks.
Yeah. So basically, the tank is comprised of multiple blocks in order to fill the circuit capacity. So if you have enough transactions inside the block, then the block becomes a tank. Okay, so it's kind of an intermediate, like plastic construct that's going to go away once you have enough volume.
And then the chunks are proven by different provers in the prover network?
Absolutely.
Okay, and then last part of the understanding here is there an aggregation of the chunk proofs that happens?
Yes. Once you have enough tanks, enough blocks, basically there is an aggregator that engages that picks up all the ZK proofs from the individual components and creates an aggregate proof, and this is what gets submitted and verified on L1.
Okay, so that's the question. Is this a centralized person? And if
No.
It's one of the other
You just
proofs.
pick it from the same prover set, basically.
Okay, so for each batch, so set of chunks,
Yeah.
you allocate an aggregator similarly to how you aggregate
Yeah.
a prover.
And you can even go further and potentially in the future not aggregate one batch. What chunks for one batch would aggregate for 3 or 4, even 100 batches. It's just that at the moment, it's the most optimal approach is to aggregate for one batch, but you can see how you can expand it and do it for multiple batches.
Gotcha.
Oh, you remember it?
Yeah,
Good.
I remember. Are you kind of not concerned about the complexity of implementing like a consensus algorithm on the L2 to make this all work?
We discussed that actually. Yeah.
So that's why basically in a way, in terms of how we launch this to the market, basically if we start with having the full decentralized network with the validators and the consensus and everything, then it's going to take us like a year to go to production. If we start with what we have now with the centralized sequencer effectively, but decentralized the prover network, then we can launch in 6 months, which is like a big difference. And not only that, is that no matter what approach we take into decentralizing the builders, okay, the prover network is more valuable because that's where the value is. We create value in a valuable network, we can easily transition to whatever sequencer technology we adopt in the end, right? Not even sequencer, we don't like this term anymore, builder technology.
One thing to also consider is that we discussed it already, and I think if we go with the consensus route, that's the way we're gonna go about it, is we'll just verify the attestation for each round in circuit, rather than publishing and verifying it on an L1. That'll make it a lot cheaper. You'll still have a bit of overhead in terms of like tracking the sets and everything, but it's gonna be nothing compared to like verifying an actual certificate on the L1.
I just mean the complexity. Yeah.
Oh yeah. The computational complexity is there. Yeah, I thought you meant more on the cost side.
It's not just the computation complexity, it's also the communication complexity, but it's everywhere.
Is it fair to say that you just said that the values in the proving network, is it fair to say that you think more value is going to be captured by the proving network? Because, from our perspective, it seems likely that most of the value is going to be captured in the block building from the builders.
You're talking about the economic value. We're thinking about in terms of like the social value in a sense, because this is what allows you, if you have a proven network, this means that you can achieve higher throughput, higher robustness, and have mindshare and build a community. And
but also value as well, though. If you implement PBS, like for example, if you look at Ethereum now, the majority of the profits that are generated by the builders go to the proposers. Yeah. So you can see how the same can be replicated on the L2. Similarly, obviously it's not going to be the same.
Yeah. So
is that true? Because like it works on Ethereum because the proposer has the right to sell the block. The proving network doesn't have the right to sell the block if you're giving it to the builder.
I'm not sure what you mean by that.
So on Ethereum, I'm the proposer, and I've got MEV boost running over here.
Yeah.
You come along as a builder, and you say, hey Joe, do you want to do your backup block, or I'll give you 10 ETH to put this block on chain? You can only do that because I'm the current proposer. But if you remove that role...
But we do have that role. So yes, essentially the same prover that is selected to compute the validity proof is also the one that acts as a leader, so essentially as a proposer.
But I guess maybe to kind of reiterate this point, maybe, in a sense, like you have a strong monopoly by the sequencers to basically perform whatever sequencings of that specific block, versus if it is just a prover, I mean, they don't have much controls over the sequencing of the blocks, and that they don't really have that kind of monopoly over the block as well. So to that point, I do think that the sequencer has more monopoly.
But does that really matter? Does the proposer have a monopoly on Ethereum, like at each slot? Does it? Well, I mean, only for 12 seconds. But you can emulate the same here, where the prover that is assigned the leader role for the given block has the monopoly, so they can choose whatever block they want to include. So it's the same thing here. I don't see how it's much different.
But don't you post the call data before, so it's kind of committed into it?
The data is committed after the block is proposed.
So you propose the block, but then you verify. I mean, you run the proof right after, right?
Absolutely. We have the concept in the fully decentralized design. We have the concept of block reveal. So basically, initially, the block builders submit bids. Basically, the proposer polls for bids from the builders, and once a builder is selected, with an appropriate right, if you like, then the builder is committed to revealing the block. So no one can sell you a block.
Okay.
Also, as we mentioned, like because you will implement hot stuff for consensus, doesn't that also mean that whether or not prover actually does the job or not, it's more of a latency delay. Hence why I still believe that the sequence
latency delay for what? For block confirmation or for proof?
For the confirmations of the proofs.
But the latency is a few seconds at most, especially in hot stuff, since it's.
Oh no! I mean sorry. I mean like because as you mentioned, if someone is censoring the provers and that they're bribing the proofs not to submit the blocks, not to submit the proofs, let's say, in that case, because you have a hot stop, that you still have pre-confirmations at each checkpoints, right?
Yeah.
And as such, prover doesn't really have that much leverage to say that, okay, this block cannot be produced. It's just that if they are censored, that provers doesn't do the work, blocks just gets finalized a bit later in the time. So in that sense, I still think that the sequencer would have more monopolizing power over the block production.
But I just don't see how it's different to Ethereum. So let's say in Ethereum right now you have 1 million validators. Each validator is assigned, has a monopoly over ordering essentially for 12 seconds. And you have the same thing. So Ethereum, you can think of Ethereum's consensus in a similar way where it has the finality, but it's essentially Tendermint, but the voting is stretched out across 2 epochs rather than within one slot. And so I don't see how you get different properties if you use provers here rather than.
Oh no! I was just responding to the point that you mentioned about how prover is kind of more of a monopoly over compared to proposers on PBS.
Oh no! I wasn't saying that. I was saying you can think of provers playing a similar role to what the prover the other way around. So you can think of the prover playing a similar role to what the proposer plays on L1 in this specific part of the book.
Yeah, and which is something that I was disagreeing on.
Okay,
Yeah.
I don't see a difference, to be honest.
Yeah.
I think.
Yeah. Just so I understand, so you give one prover the right to pick a block based on the
First law. Yeah.
Sorry, this scheme of removing the sequencer altogether from the picture, it's clear that it works with L1 scheduling for picking up a prover. Does it also work if you have proving bidding, like the other approach that you presented?
I think we can make it work, yes.
Great. Thank you very much for a lot of stuff there, but
Thanks for having us.
Yeah, thank you very much. Okay. All right. So this is Joel, and then this is Cooper. Enjoy.
We also have Santiago over here.
Sorry, Santiago. Right, there you go.
Yeah, no worries. So yeah, we're going to talk about decentralizing Aztec's proving network.
I'll see you later.
We'll wait for Elvis to leave the room. That was a very good talk though, and actually it helps me speedrun my talk to get to the interesting bits. So shout out to the Scroll folks for setting us up nicely. I'm Cooper, I'm a product manager at Aztec. You have Joe, our co-founder and president, and Santiago, who's one of our engineers. And yeah, for those that don't know, Aztec's a privacy first layer 2 on Ethereum. That's our new tagline and we're sticking to it. If we change it in a few weeks, don't ask me about it. Aztec, also the privacy first layer 2 for Ethereum, supports smart contracts written in Noir. You may have heard of Noir. And it enables both public and private on-chain smart contract composability. You can try it today. The sandbox is out, you can write your contracts and start building stuff. But yeah, so the agenda today, we'll talk about why decentralized proving, we'll talk about Aztec's prover coordination, request for proposals, and we'll talk about what the future kind of looks like. So similar to Toghrul and Scroll, we see 3 kind of major reasons for decentralizing proving. The primary one is censorship resistance. If you're building a layer 2 with an enshrined prover, they can censor the whole network. And if it is whitelisted and or the only one who can actually submit those proofs on chain, they can censor the entire L2 and prevent it from producing blocks. Similarly, that affects liveness. In the event that provers drop off the face of the earth, that halts block production and takes time to deal with. And so that results in worse user experience, among other things. And then it's also really important for credible neutrality and I guess the vibes of crypto and what we're all trying to achieve. The idea that any centralized proving network who has a whitelisted prover can make arbitrary decisions that might be in their best interest, but not in the best interest of their community and those people building applications on top of that network is something that actually distributing and decentralizing your node infrastructure can support. It supports credible neutrality, pumps the vibes, gets people involved in your protocol. So these are.
I'll just add one thing on censorship resistance. Like as a privacy network, we can't take the view of like progressive launching with centralized sequences. The censorship resistance kind of portion is the thing we try and prioritize above all else, just based on kind of how we've seen the world react to privacy protocols. Is all I'll say.
Yeah, and so you see Scroll, you see other projects talk about, we can decentralize in phases. For Aztec, these are day 1 mainnet requirements. And so why aren't we there yet? Honestly, it's hard. It's harder than other challenges. A lot of people are talking about decentralizing their sequencing now, which gives, better censorship resistance guarantees in the L2. You don't have to use forced inclusions or forced transactions. You can expect an honest proposer to come through and put your transaction in a block. So decentralizing sequencing maps really nicely to L1 PBS and all the work that has gone into decentralizing L1s for years. This is much more analogous to decentralizing compute networks or other types of things, and so there's less historical work for decentralizing proof networks as well. We can take lessons and topics from other things, but it's fundamentally kind of a new challenge. And then I would say the other thing is lack of social pressure. Like a lot of people are using L2s right now that are fundamentally centralized, that aren't censorship resistant, and they're putting hundreds of millions or billions of dollars into them. If that's the case and people are adopting them, what incentives do projects actually have to decentralize? it takes customers, it takes people in the community, it takes people actually advocating for those rights and those requirements in their protocols for them to get implemented and have research and put money into adopting them. And so, how do we get there? What can we do about it? We can do open research like what we're doing right now. We get here, we talk about it, we get people aware of the fact that you actually need someone from the community advocating for these things for them to get adopted into protocols. Open source code, don't want to name any projects, but a lot of proving systems aren't open source or are actually open source after they've been in use for a while, which is interesting. And I think we do need to be very proactive in applying social pressure. There's two ways where we get censorship resistance and decentralized L2s. One's proactive with people like us advocating for it and encouraging teams to take these things seriously. The other one is something really, really bad happens and you either become decentralized or you die. And so we really think that, the people in this room specifically and those at DevConnect need to be more proactive in actually asking for these things, otherwise we may never actually get there. How is Aztec helping build this future? All of our major network design decisions are gone through a public RFP process. We have an outstanding question, we put it up in an RFP, we make a decision, consulting with industry leading experts. Hi Yuki. Yuki's been super helpful in all of these RFPs that we've done, among others. Eventually we'll ship an open source reference implementation, and at the end of the day, Aztec really believes in social consensus, and so it's up to the community of node operators to actually agree on these changes and think that they're better for the protocol. We can't force them into it, among other things. I'm also speedrunning this just because Toghrul talked about a lot of these things, so we can focus on the interesting design aspects. So we did a sequencer selection protocol, which was actually written by Santiago, very similar to what Toghrul and Scroll was just talking about with the random VRF-based leader election. We currently have a RFP for upgrade mechanisms, so if you're interested in designing blockchain governance, upgrades, decentralized L2s, submit a design by Friday. If you have a good idea, let me know, maybe we'll extend it just for you. And then we currently are in the decision-making process of our proving network, and so this is what we're here to talk about for the rest of the time. Highly encourage you to go to forum.aztec.network if you're interested in the upgrade RFP. There's about 9 designs out there right now. Joe, you want to speak to the requirements, or Paula?
I can maybe start. I think one of the key differences to public L2 is just thinking through what a transaction is. So before I dive into these, maybe just kind of explain how Aztec transactions work. So an Aztec transaction is a zero-knowledge proof. It's about 25 to 60 kilobytes. We're not quite sure yet, but it's quite big. So it's not just a signature and a request to perform an execution. It is the execution and then a proof of that execution. So there's a big difference there. And that affects how we do sequencing and proving, because if you have a private mempool and no one gives you those proofs, you have a very bad data availability solution, and it's a lot worse than the one on public L2s. So a lot of our designs are kind of done with that in mind. Maybe Santiago can go through the core elements that we've done. Just wanted to get that out there first.
Yeah, absolutely. It's basically focusing that this prover network design is compatible with what our sequencing algorithm we have picked before, which goes in line with the requirements that George just mentioned. We'll focus for sure on permissionless, given that we want an open network where everyone can participate. And I'm going to skip a couple, but mostly focus on graceful recovery, real resilience, and basically with the ability to upgrade and incorporate future improvements in cryptography, because we know this is a field that's changing constantly, and we want to be able to leverage new improvements in cryptography so that we can speed up the proving network.
Yeah, and so these are just kind of things that we keep in mind as we walk through all of the designs that we've had today. These are the things that we prioritize, and if your proposal didn't match any of these requirements, it probably isn't up here today. We ultimately saw 4 categories of submissions. You can see there's an x-axis, which is you can have a cooperative or competitive network. Cooperative is what Toghrul and them were talking about, where you divvy up the work among nodes. Competitive nodes are either working against each other in auctions. And then once you choose this, actually maybe a first question is if you want to enshrine it or not enshrine it, which goes back to the PBS debates. And yeah, so we received 8 plus submissions potentially. We got a few, shout out to Ellie and the Espresso Systems team for their submission, and then we actually got one about staking reputation and proof races from a few people at the Ethereum Foundation. If you're in this room and you contributed, I appreciate you. And then, yeah, we'll talk about some of these today and their trade-offs and where we landed on these design spectrums. But all of these are published proposals at forum.aztec.network. You can read 9 different ideas for how you can decentralize proving networks. As far as I know, it's one of the biggest bodies of literature on the topic. So Joe, we'll kick it to you to talk about cooperative designs.
Yeah, so maybe to start, so an Aztec block has a 2x2 binary tree structure. So I'll go through that first and I'll talk about how a cooperative network works. So you can see down here, the base level is transactions, and we kind of have what we call a base rollup circuit, which takes 2 of those transactions and puts them into a mini rollup, and then we kind of aggregate up the tree until we get to one proof. And the tree's designed like that just so you can have mass parallelization across lots of different machines, and kind of really speed up the time it takes to generate these proofs. And so the cooperative design was kind of like looking to take advantage of that and say, okay, how can we look at a staking set and how can we divvy up this work based on kind of a VRF, similar to what the Scroll guys were saying, and assign parts of this tree to individual provers so everyone could participate in block production. And so we had about 3 designs in this category. I think the one that was written by me was a staking proving network. It basically took the opposite end of the VRF to the sequencer selection algorithm. So the sequencer is the high VRF, and the bottom end VRF outputs the provers. And then you kind of go through this and you just assign parts of the tree to them with some redundancy to produce the block. And so based on that, we were able to produce a block in a cooperative fashion, divvy up rewards based on that. And it was quite an elegant design, but I think we can get onto one of some of the reasons afterwards, maybe?
Yeah.
Great. Let's get it.
Nice. And so yeah, this is one category of ways that you can decentralize your proving network. You can build kind of a BFT style network where you can have n layers of redundancy giving you 33 or majority assumptions. And then competitive designs, we'll get to Paula.
So competitive designs is clearly the opposite. Basically, we want to set up some sort of auction where the different provers will compete against each other for the right to prove that block and basically get a reward back from that. We do not plan to go with something like proof of work here or proof racing in the default case. We agree with Toghrul and the guys from Scroll that that's mostly weighted effort. That said, competitive designs work either by themselves or also a very, very useful fallback mechanism if something is going south. Like if for some period of time we don't see, I was right. If for some period of
copy?
I would definitely bring down an article on that. So if for some period of time we don't see any blocks, we can fall back to a competitive design, even something like a base design, where basically it's free for all and anyone can submit a block. The 2 main differences that we have explored across competitive designs were regarding whether we enshrine the auction or not. So basically we have one option where we enshrine the auction, basically the category, the conditions in which the provers are going to submit their bids and how they are selected based on that, versus, it's completely out of protocol. The Fernet sequencing protocol elects a single leader per block. So in an enshrined mechanism, what we have is the sequencer being completely free to choose whatever prover they want to go with, and we expect in a competitive design just for provers to submit bid of protocol, so that sequencer having complete freedom to design which one they want to go with.
Yeah, and on that note, you can see in this diagram we have like an enshrined version of an auction. You have the L2 node, they're submitting bids which could be positive or negative based on how much they expect their block rewards to be. Could be inflationary or deflationary, and at least in this design it's all, you can see, on L1. But what does the future look like for Aztec? Paula, you want to take this one?
Sure. I think we can talk a bit about pros and cons of competitive. Competitive has the advantage, and I hate myself for saying this because I submitted a cooperative one, and the left in me loves the cooperative one, but how? Basically, competitive pushes participants into improving the services they are providing. And right now, with so much room for improvement that we have for getting better proving times, proving reliability, lowering costs, it makes sense to push for this competition. Also, having a competitive design, in particular an unenshrined one, allows us not to set the parameters by which a prover needs to be selected. What I mean by this, if we enshrine an auction in a competitive design, we run the risk of overlooking certain parameters. For instance, if it's an auction just based on cost, we could run into provers sacrificing speed or sacrificing even reliability, which could hurt the chain in certain situations. So for now, what we're considering is leaving the criteria for this competitive auction out of protocol so we can iterate it faster. So the idea is not having this role of prover as enshrined within the Aztec network, but rather having them participate and approach sequencers, or the other way around, with their bids for creating each of the blocks. Do you want to introduce Seun?
Yeah. So this is one of the designs that was submitted by myself, actually, that facilitates an out-of-protocol RFQ or auction. Kind of depends what standards emerge and what economic guarantees the sequencer actually wants. But you can see on the far left, you get a proposer with a couple VRFs. That's the Fernet sequencer selection algorithm. At some point, you have a prover commitment phase, which requires the sequencer to choose an Ethereum address. And it also requires that Ethereum address to put up some stake that could be slashed. And you can use that acknowledgement of them putting up stake as a form of what I would call a minimum viable payload timeliness committee. Payload timeliness committees are something that's part of the Ethereum PBS research, and Mike Nutter has a few papers on it. But it's a way that we can actually prove that this proving network or this individual actually believes that they have all of the data required to actually prove this block. If they do not have all the data required to prove this block, they are unlikely to put up stake that will be slashed if it doesn't get proven. And so in that way, we can actually not build this massive consensus network that's attesting to data availability. We can just use a very simple commitment and slashing scheme. And so, we do imagine that this is facilitated via an out-of-protocol version, kind of like MEV Boost. Maybe you call it Prover Boost. I'm open to really good suggestions for names if anyone has one. But we do see this to be kind of a nice new open source software that will have a relay ecosystem, et cetera, emerge, kind of like MEV.
I think
I was going to say the reason we need this is because if you don't have a system where you can just keep running ahead on the L2, and a guarantee that the L1 validating bridge will eventually catch up, you just end up in a world where you can kind of have huge MEV attacks. So a block on Aztec has a finite proving window. In that time, it must be proven on L1. So this kind of prove a commitment and prove a deposit is that kind of bond that says the proving entity that's picked, it could be NAIL, it could be a third-party marketplace, is confident that in that window they can actually prove the block, and it's kind of key to making sure the network has liveness.
Yeah, I think that the elephant in the room regarding going with a competitive design is monopolies, the risk of monopolies, especially if we unenshrine the selection. We had some proposals that enshrine the auction process, which by relying heavily on cycle-resistant mechanisms, modify the rewards to make sure that different participants were selected, even within a competitive section. Still, we prefer to keep that out of protocol so we could iterate faster and simplify. And the reason for that is that though we think that there will be forces for centralization, the barrier to entry should not be that hard in the sense that it should be feasible to spin up the necessary hardware in order to participate in a proving market. So that should at least mitigate these risks. We're also relatively fine if we have not a massive amount of different provers. And we also see a situation, as the scroll guys mentioned, where we start to see vertically integrated sequencers and provers. Basically, sequencers that are actually backed by a builder, and the builder also taking care of the proving. So that would naturally generate some diversity among the proving sets. And it also allows us to slightly increase the requirements for the provers if we go with a fully cooperative design. we want people to be able to participate, which means we need to place relatively low hardware requirements on provers, which is what led to the binary rollup topology that Joe just presented. But if we go with a competitive design, maybe we can crank things up a bit, we can go with a higher rarity tree, and we can actually start compressing and flattening the tree, which even though it lowers parallelization, it also lowers total latency and reduces total coordination between the nodes, which to the end user means less times, less cost, which is probably what the end user is about, and they don't really care that much about their request being served by 5 provers or 5 branches.
Yeah, so this is also competitive purely on price. It's not a latency game. Like if you make this fastest prover wins, you get in a whole world of pain where you have very large hardware and people are competing to kind of win that right based on pure latency. In this case, it's cheapest block wins, and because the network is specifying the time limit under which that must be proven, you actually incentivize proving costs to go to 0, which is kind of what we all want, because it should be the smallest part of that transaction.
Yeah, and so you can see here, I'd say we may actually be taking an opposite approach to Toghrul and Scroll in the sense that we really prioritize fully enshrining the decentralization of our sequencers through the Fernet random leader election algorithm. And at this point, it's totally up to the sequencers to choose what makes the most sense for them. For certain sequencers, let's say your Coinbase Cloud, your Figment, you have a significant amount of hardware. It does not make sense economically or even for the protocol for you to force that being outsourced and share all of those transactions with n numbers of provers. In a worst case scenario, you could have a proposer who's building a block that's entirely from a private transaction mempool, and if that is Figment or Coinbase or someone who has enough access to compute, there's no reason that they should be forced to share all of those private transactions and private transaction proofs with everyone before the proof actually gets generated. And so this is nice where it doesn't enforce high networking or high data requirements on, let's say, thousands and thousands of machines. At most, or at minimum, you have 2. You have whoever's doing the proving. You could actually just have 1. But you could just have whoever's doing the proposing, and then they can be a vertically integrated prover as well. And so it's really nicely giving you that flexibility and not enforcing the whole network to kind of share these networking costs, which in our case could be very huge. You could have blocks of hundreds or thousands of private transactions that could be 32 kilobytes each. And so it also nicely addresses the proof withholding problem that non-privacy networks don't have. So yeah, we actually are just gonna open this up. I'm gonna ask my colleagues a few quick questions here. And so we've kind of mapped out all this space. What are kind of the biggest challenges when deciding on an architecture? Maybe we ask Paula first, like from an engineering perspective, what is the biggest motivating deciding factor if you're watching this or listening to this and you're like, I want to decentralize my provers, which of these options should I pick?
The first deciding factor is how easy it is to code, basically, from an engineering perspective. As much as I would love to be coding this for the next 5-10 years and have all the time in the world, that doesn't fly, and besides we want to get something out there as fast as possible to start actually battle testing it. Effort of implementation is one of the main drivers, both in terms of time and simplicity. I firmly believe that design, as the more simple it is, the easier to understand, and the more secure and reliable it's going to be. And also another important point is the ability to iterate it. We want to make sure that if we enshrine something, and enshrining then it's maybe a bit difficult. So we want to start slow, keeping things out of the protocol if they don't really need to be. And like shout out to the minimum viable enshrinement by Vitalik going a couple months ago. So we can iterate faster of protocol and only get it inside as part of the protocol when we're sure about it and when it actually makes sense and not before.
Yeah, you can always add more formalization later. It's actually really nasty to remove formalization from some of these things. Joe, from like a business founder project-based consideration, what was the biggest challenge on deciding?
Yeah, I think some of the points that the Scroll team made about kind of people wanting to own the network is one that resonated when we're thinking about the cooperative networks. If you kind of don't have a decentralized sequencer and you don't have a decentralized proving network, it's very hard to kind of let people feel like they're a part of the network. So we were kind of considering that, making sure that we could grow to a large enough sequencer set when we were making these trade-offs. I think also just making sure that the core values of the network came through these designs, and ultimately we picked a design here that really favored censorship resistance and liveness of blocks. Like we want there to always be an Aztec block and not have delays. So the design is really it really favors those properties. In fact, there's even a backup mode to make sure we always get a block to enforce that.
What are the trade-offs here between, you talked about enshrining and iteration, but maybe what are the trade-offs between cooperative and competitive designs?
I think that what Joe mentioned, just mentioned regarding involvement of the community and like how you involve, how diverse you ensure that your set of participants is, and that relates both to community engagement, social consensus, and what Scroll guys were talking about, social value, and also addressing censorship resistance, which is also an important point. I think those are some important points to consider, and also latency and cost requirements. If you have maybe high enough transaction volume so that you can amortize total proving cost, then you could sacrifice a little bit the efficiency of a competitive design. And also, if you have other forms of finality that don't depend on a proof being submitted to L1, you could also delay the time of the proof, not indefinitely, but long enough so that improving latency is actually not a requirement.
Yeah, that makes sense, like the batching and chunking that Scroll was talking about earlier. Joe, we've been working on this for a while. I saw a talk from Zach in 2019 talking about this 2x2 rollup structure. What do you wish existed back then, or like what resources do you think that there'll be for decentralizing proving in the next 12 months or so?
Maybe I'll answer it in a different way. I think the known benchmarks about your proofs ahead of time is very helpful when designing this, which is hard when you're kind of building the train tracks as you go. So if you don't know how long a proof's going to take, it makes it very hard to design a proving network. So we've had to iterate along the way based on getting that information. But in terms of resources, I think, yeah, it's always useful to start with a framework of the design space, because otherwise you're going to end up with lots of the same designs, and you really want to explore the design space, not get 4 of the same designs. So knowing that kind of cooperative, competitive, enshrined design space ahead of time lets you fully explore it, rather than kind of just focusing on one segment that aligns with your own lefty interests.
Yeah, I'm excited for free product idea for anyone hacking this weekend. If anyone wants to fork Tindermint and implement something that distributes like proof work to proving marketplaces, that's probably a good product idea. But yeah, that is all from us, I guess. We will do questions from the audience for 5 or 10 minutes. But if you want to join the Aztec community, Discord, really good documentation that outlines the entirety of our private execution environment and our ZK rollup. You can download the sandbox and start writing Aztec Noir contracts. One of the first times ever in the world you can write public and private composable smart contracts. And follow us on X, Twitter, whatever. I don't know what we're saying these days, but follow us on X. Yeah, thank you. Yeah, questions? Yeah.
I'm just curious on like more holistic view. Like, it would be interesting to know like who's the client of the sequencer. Is it the user straight, and then the sequencer? How long does he have to actually sequence the transaction before these are? Before he has to choose the best bit, basically.
Yeah, maybe we can run through how the network.
Okay, sure. There we have an initial phase, we call it the proposal phase, where sequencers with high VRF rankings submit a hash of the block that they want to propose. Out of that set, the one with the highest VRF wins, and then we go into what we still need to exactly figure out, which is a mix between prover commitment, deposit, and reveal, where we expect the sequencer to, once the block has been committed to, pick a prover, have the prover place a bond on L1 to say, hey, commit to prove this, and also the sequencer to eventually reveal the contents of that block to L1, so other clients we ensure that other clients have access to it and can have some form of pre-confirmation, assuming that they have individual proofs to verify. So yeah, basically sequencers, the first thing they do in this block building phase is commit to a particular ordering of transactions.
And so the prover has no liberty in adding anything to the sequence transactions, right? This is a fixed set.
Yes.
Okay.
I guess one thing to add as well, different to kind of the Scroll guys, all of this happens on L1, so there's no L2 consensus. The whole
very based.
Yeah, it's based with a few rules to make sure things happen correctly, but it's the only way we can get the same censorship resistance properties as Ethereum.
So many large rollup that currently they have centralized sequencers, and they defend them by saying that, well, you can always have this forced inclusion on the layer 1 to avoid all these problems. So from your perspective, we want to defeat that argument. I want to see what is the most strongest argument you would have, or maybe arguments that you will have.
I'd ask them if they want to run an Aztec sequencer.
I would say that right now, a lot of forced upgrades actually aren't enforceable. I'm giving a whole talk at L2 Days about this, but taking a popular network that doesn't have fraud proofs yet, they can actually just ignore any transactions in the forced delayed inbox. So you actually don't get censorship resistant properties by having a forced exit feature by itself. You also need fraud proofs in optimistic cases or valid zero knowledge proofs, and you also need non-quick upgradability. You can still get censored in L2 networks that have instant upgradability, because if they see a transaction they don't like in the delayed message inbox, they can just update the implementation of the network and ignore it. And so I would say that you are not getting very good censorship resistant guarantees in almost any L2 right now, besides maybe like Fuel V1, among others. And so I would look more critically about what you want censorship from, and if it is possible that your applications that need to be censorship resistant can wait 24 hours every time that they want to get a transaction in, and then wait 7 more days to submit a fraud proof and guarantee that their transaction was actually forced included in the network. And so for most use cases, waiting 24 plus 7 days, 24 hours plus 7 days to get a single transaction in is something that would fundamentally not be viable for, you know, a majority of use cases. It would work if you need to get your money out, but then you're just never using that network again.
Forced inclusion is a second-order citizen.
It can be a first-order citizen if you have a decentralized network that enforces it, but yeah.
Well, not on L2 right now, so.
Yes, not right now.
Any other questions? All good? All right, so I guess that's it for today. Thanks again for the Aztec team for the great talks. I guess thank you very much for the protocol coordination problems. And I guess I also want to thank everyone for coming in today, sticking around until like 10 p.m. for this research talks that great speakers have given out so far. So again, I really appreciate that people came over and participated, and also thanks again to a lot of the groups that have supported and built this event to this day. Now, we do have 3 more workshops coming up, so if you guys, anyone who, well, not today, obviously. Not today, please. But for tomorrow and the day after, for Tuesday and Thursday and Friday. And just to kind of like, you know, show that a little bit. So for tomorrow, it's gonna be PBS, MEV, order flow type of stuff. So maybe a little bit related to crypto coordination issues around MEV, but it's gonna be a lot more PBS type of things. On Thursday, we'll have a bit more heavy focus on privacy related stuff, and we'll have a lot of people working on privacy space also come and join on the conversation. And then on the last day, Friday, we'll have data storage, I think, which I think is a very underrated topic, frankly, very important on the blockchain space. So yeah, please join, check out the Fenbushi Twitter, and we'll have all the links there, so you can just find the links and join there as well. So again, thank you very much for coming, and that's it for today. Oh, I guess one last thing. No party, just research. Thank you very much.